The challenge in meshoptimizer is how do you build a library that's useful, given that there's so many different ways to actually implement the rendering part. If you have seen an index once, if you're ever going to see it again, it should happen soon. How soon is hard to answer. You split the mesh into clusters, and then you take a bunch of clusters that are near each other. You take them out of the mesh, then you simplify the result. You simplify the result in groups of clusters. You get fewer triangles, and then you split the thing back into clusters. You put the resulting clusters back into the mesh, and then you repeat the process.
So, maybe we can start then. Tell me high level overview of meshoptimizer.
Sure. So today, meshoptimizer is like 3 projects in the trench code. It started as just one, and this is kind of where the name comes from. But there's a couple other satellite projects that we may talk about in the future. But so the core idea, right, is it's a library. It's a C++ library that, surprise, optimizes the meshes for you. The core reason for the library's existence, I guess, is that when people think a mesh, even people who are familiar with 3D graphics, they think of a mesh as maybe you have a vertex buffer and an index buffer, but you don't think too much about kind of what is inside the vertex buffer, what's inside the index buffer. Do things matter? Like, does the order of vertices matter? Does the order of indices matter? Does it matter what representation you use for individual components? And so typically when you start a new engine, or even in some production high-profile engines for many, many, many years of their existence, you could have a very inefficient sort of set of data that you prepare, you take your mesh from like Maya or Blender or whatever, you bring it to runtime as a vertex buffer and index buffer, you send it to GPU, and you think you're done. So the problem is you're not done. And kind of 2 things are important. First is for people to know that there's like extra steps along the way that you ideally should do for things to work fast. And 2, if you know that these steps should exist, kind of what do you do? Because usually, building engines, building games takes forever. Every extra step you add there is like, do I really want to do this? Maybe things are fine as they are. So meshoptimizer is basically kind of 2 things. First is a statement, no, it's not fine. 2, for it to be fine, you should use the library.
Hi everyone, let me take a break to thank members of the show who made this conversation possible. Members get earlier access to videos, including longer unedited footage from live streams, as well as they're invited to our private Discord server. If you want to support the show, there is no better way than becoming a member on YouTube or Patreon. Thank you so much.
So this is kind of the reason why the library exists. Because at some point, I was working on like some engine code, and I needed a set of code that I knew had to exist, but it didn't really exist in like an easy to use form. It didn't exist in a there's some libraries that kind of try to do what meshoptimizer does. I'm biased, so I can say this, they don't do this as well, or many of them are quite old and like should not really exist anymore probably. But so there wasn't a solution that I was happy with, right? So I had to build one. So I built one, and that's the main meshoptimizer library, right? So now since then, there's kind of 2 extra projects that are part of the same repository. One is fairly old now too. It's called glTF pack, and this is the kind of connection between this world of carefully optimized, ready for runtime, native game engine rendering, and the wild west of web, where there's like an interchange format called glTF, and there people think even less about what goes into the file, because it's like, I don't know, there's like bits and bytes, and like something goes to my GPU, and I just open it in 3GS and render it, right? So now there's glTF pack, which is an application that takes the algorithms that exist in meshoptimizer and then like a bunch of other stuff, and prepare the glTF files for you in a way that, again, is like reasonably optimal to render. And then the final edition as of end of last year is clusterload.h, which is a solution. It's kind of Mesh Optimizer style in the sense that it's a native library meant for integrating into the engines, etc. But it tackles specifically the problem of some people call it virtualized geometry, some people call it
Meshlets?
no. So I'm blanking. Right. So the Ubisoft folks call it, I think, micropolygon. I think they have a term called MPH, micropolygon hierarchy. I don't know, but basically, Epic invented / popularized the concept of rendering like way too many triangles fairly efficiently through this use of multi-resolution data structure. They call it Nanite. And other people call it by other names because Nanite is a trademark, I think. So anyway, so the main library, Mesh Optimizer, is still kind of the main focus of the project, but there is two other satellite ones.
Okay.
And I guess maybe just to give people an idea of, so the most basic way, I guess, to explain why meshes are more complicated than they appear is actually something that probably everybody who did computer graphics courses up until the point where you have to like render real geometry probably faced. So like you have a cube, and the cube has 6 faces, but GPUs don't really render like polygons, they render triangles. It has 12 triangles on the faces. Cool. And then you ask people, well, what are the vertices of the cube? And they say, well, there's 8 vertices, right? Because there's 8 corners of the cube. And then you look in various runtime-ready graphics formats like glTF or whatever. You open a file, you look how many triangles does it have, 12. You look how many vertices does it have, and then it's like 24. And you expect 8. And immediately like it becomes clear that something is wrong here. So the problem is in graphics. The first problem is in graphics. The vertices that we talk about have attributes. So you have position, but you also have normals, texture coordinates, etc. And there's the terrible problem of attribute discontinuities, where a given vertex can have multiple attributes. So for a cube, if you think about the corner of the cube, it actually has 3 normals for a flat shaded cube, because the normal kind of associated with every face of the cube points directly orthogonal to the plane of that face. And so in computer graphics, the way GPUs work is you don't have like 8 positions and then a bunch of other normals that are elsewhere. You have everything jammed inside a single vertex. And so because of this, you have, for a cube, 24 vertices. But you can also say, oh, the cube has 12 triangles, and every triangle has a vertex. So you could represent a cube as 36 vertices, just 3 vertices for a triangle. And so there is a lot of different ways to kind of represent a single, even in the basic model of just vertex data and index data, there's a lot of ways to represent a single mesh, right? And so what you get out of your model files from Blender or whatever is usually a representation that may not be optimal, even from the perspective of how many vertices does it have. Right, and then there's like other stuff around GPUs that we can get into in a minute. But yeah, this is kind of the basic idea of the library.
So the basic idea for anybody who has their own engine and they want to load the model in geometry to call into a mesh optimizer and call a couple of functions in sequence, so you kind of have the structure, the vertex and index buffers optimized, taken care of, and you don't need to worry about it too much.
Right. This is an important distinction to highlight. So Mesh Optimizer is a collection of algorithms, and it's sort of like it's tools to build something out of. It's not an off-the-shelf kind of end-to-end solution where you just feed it a Blender mesh file and something ready for rendering comes at the end. And it's very, very intentional because, so here's the kind of the problem with Mesh Optimizer. There's many different engines, and there are certain things that are very common between the engines. And there are certain things that most engines share, although this becomes, even like mesh rendering after Nanite and after some other stuff before this, even that got very sort of complicated, that you could have very different approaches that are used by different engines. But there are some things that were relatively common, but there were many things that were very different between different engines. And the challenge in meshoptimizer is kind of how do you build a library that's useful, given that there's so many different ways to actually implement the rendering part, right? And so the answer is the algorithms that meshoptimizer provides are all composable. So it's like, oh, your pipeline for optimizing mesh is like 10 stages, and like 9 of them are, I don't know, meshoptimizer function calls. And then the 10th one is preparing, like, for example, I mentioned that the vertex data, right? So you have positions, and then you also probably have normals, you probably have textual coordinates, you may have some other stuff. Different engines have wildly different ways to represent this in memory, because you could have full floating point precision storage for some of these, although bad engines do this. You could have half precision, you could have integer quantization, you could have crazy bit packing methods where you say, oh, I don't know, my normal is like 2 7-bit components and one 1-bit component to represent the sign of the third component. But I will place this 1-bit component next to some other bits where I store position data in, just because things are, when you deal with compressed vertex representations on the GPUs, you want something that's easy for the shader to decode. And the shaders don't really do even unaligned byte reads very well. Definitely it's more difficult to do sort of bitstream extraction in the shaders. And so you try to pack things into byte or 2-byte or 4-byte sized quantities, right? And so you jam things together. It's like, okay, 10 bits from this component and 10 bits from that component and 2 bits from this component go together, and it's all smooshed, and then the shader decodes this. Cool. So there's no way for me to, there might be a way, but I really didn't want to, let's put it this way, to deal with this sort of diverse situation in the library, right? So because of this, meshoptimizer doesn't really have a vertex format. It doesn't care. It's up to the engine to decide kind of what the optimal set of attributes, etc., is and how to pack them. But then a lot of the other code around this is in the library. So yes, you have a pipeline. Most of this pipeline is hopefully meshoptimizer calls. Some of this pipeline is custom. And then you run this to take your mesh from the unoptimal representation to the one that you can pretty much directly feed to the shaders at runtime, and then sort of render from that.
Regarding the types, this means that your library is, as far as I've seen, templated, right? You can have templates for types.
Okay, so yeah, let's briefly talk about the language choices. So the library is in C++, it's written in C++, the implementation is all C++. The interface it exposes is actually mostly C. This is important because you can use the library from other languages. It's very, very painful to bridge C++ code across the language boundary. It is not painful usually to bridge the C interface. meshoptimizer has Rust bindings, it has Zig bindings. I'm sure people wrote bindings for other new cool languages. It has .NET bindings. Anything that's managed, so .NET is a good example. You have an FFI layer that you use pinvoke to bridge calls from the .NET runtime. And if things are very neatly C-like, you have arrays and sizes, then it's very easy to bridge a call through pinvoke. If you have a class in your API, God help you. So because of the complexities like this, and also because I like short compile times and all of that good stuff, so the interface is almost completely C, with one exception. So the thing you're talking about is when you deal with index data, people can't agree on sort of the size, the types of that index data. The most basic problem is you can have 16-bit or 32-bit integers. And also some people use signed integers for some reason for their index data in their mesh processing code. So I have template wrappers around many functions that hide the distinction between the types of the index data, but the actual sort of core interface is just C, is just for this it's 32-bit data. And then for things like positions, for example, it would be good to call out. So my expectation is that your runtime data is carefully bit-packed positions. with like, whatever you like half precision, like integer quantization, whatever. Some algorithms need access to actual position data in floats. And so that's what they get. They get floats. And then your pipeline usually would have, at some point, it would drop the floating point position data and convert it to sort of your optimal bit-packed format. But then if you ever need to call meshoptimizer algorithms on it, you would have floating point data kind of on the side that you don't save to the runtime ready file. You just have it on the side to feed it. But yeah, so most of the interface is C. And in fact, this is... it's kind of it restricts in certain ways, of course. I don't know. I can't have default arguments for functions because everything is like explicitly it's C ABI. Oh, and also it's not just CAPI, it's CABI binary interface, meaning so nice libraries are libraries where you can update the library and then the update just works. This means the code compiles without changes, so that makes sense. But also, if you aren't using C++, this means your binding layer should ideally just work out of the box. So if you ever have a function, in C++, if you have a function and you're like, oh, let me add one more parameter to it, you're like, okay, sure, I'll just add it. Oh, the source code breaks. Oh, I'll just default it to like 0. Well, in C, the problem is you add a parameter, your binding breaks, and your binding can break in spectacular ways, like, oh, the stack layout of the function call is like different, and there's a crash that you'd never see coming and stuff like this. And so evolution of interfaces of libraries written in C is like peculiar, but this is kind of the property that I want. So going back to what I said earlier, so you have an engine, you have lots of problems, right? The last of your problem is, the last of the problems you want to solve is like, oh, how do I update this library? What unfortunately is sometimes common in game development is like you just never update code. You start a new engine, you take the versions of whatever libraries you have. They are from like 10 years ago by the time you ship a game. If you're very lucky, when you start a new game, you update them. Often you don't. So I really wanted to have this sort of property of people should trust that they can just update code. And now, do they update codes regardless? I don't know, but at least, if they ever update the code, it won't break, which means they might be incentivized to do this again in the future. But yeah, so the templates are just like, to help. There's some helpers where the library is mostly used from C++, and so when you do use it from C++, there's like some extra sort of interface stuff to help you a little bit, but it's not really super important.
Okay. So let's talk a little bit about this sort of traditional rendering pipeline, right? So the core mesh optimizer part. As far as I understand, this happens at when you create, you update the layout of the vertex and index buffers at the beginning and startup, right? And then afterwards you don't really touch them if you have static data, right? So this is at the beginning of the application, correct?
One clarification about, I guess, all of this is, so there are cases where this is not true, but most of the time I would expect that mesh optimizer used in the content pipeline. So this means, so you have a separate application, some people call it, I don't know, content baker, like mesh processor, stuff like this, right? And the job of that is to take the input file that is usually directly produced or indirectly produced by whatever software your artists use. So let's take Blender as an example, right? So use Blender. Blender saves .blend files, which is like a proprietary format which doesn't really have a clean API to work with. But you can also export stuff from Blender. You can export FBX. And so if you ever want to read FBX, then you have libraries like UFBX or FBX SDK, but never use that one. Or you can export glTF. You could export Collada, you no longer can. I think the main two interchange formats like this, I guess, are glTF and FBX. And then there's also older formats. There is a format called OBJ that is very, very popular, but it's very, very strange and sort of restricted in many ways. So it's not really a good fit for a production engine pipeline, but it's a great fit for like, oh, I want to do visualization and I just need like couple meshes. So you export the thing from Blender, and that gives you a file that you can then read. But you shouldn't read it at runtime. You could. And again, so in the web world, there's people who mostly would use glTF files kind of at runtime. But usually you have your own proprietary engine format, and so you have an application that reads this kind of sum file from the modeling application, and then does a bunch of processing to it, and this is where meshoptimizer works. So then you save a binary file, and then that binary file goes, a custom binary file, and that goes directly to your engine, like at runtime, right? Oh. Now, sometimes you may have procedural geometry. When you have procedural geometry, sometimes it makes sense to run some of the meshoptimizer algorithms on it kind of at runtime after you're done processing. And both because of this, but also because so even when you use it offline, something kind of one of my, I guess, pet peeves is some people don't treat the processing of data that happens before the engine with the same rigor that they treat the runtime. Meaning, oh, we changed the mesh. Oh, it's fine, we can wait a minute for it to like recreate the internal engine representation. So again, my opinion is, it's not fine. What you should have is the artist like changes something in the modeling program, they save the file, and then as quickly as possible, the result can be transferred into the engine. And then if the engine is running side by side with the modeling application, then you can live reload. And then it's great because you force your artists to like work within the context of the engine and preview changes to their art inside the engine, inside the game, which is how you get the best final result. But the only way that this can work is that the whole thing is fast and frictionless. Like I save the thing, it's converted, it's done, right? And because of this, and also because of the runtime use cases, in a lot of meshoptimizer algorithms, there is not just the question of kind of how efficient is the result. There's also the question of how fast is the algorithm itself run, because if it's slow, it might be impractically slow. And it doesn't help, by the way, that a lot of the algorithms that we are going to talk about today, they don't really have solutions. Some of them don't have computable solutions, as in we just don't know how to compute the optimal. And some of them have computable solutions that are like traveling salesman hard, as in like, well, the optimal way to do this is an exponential search, and it's like, there's some approximations that we can come up with. But which is actually funny. So in algorithm theory, people make this distinction between polynomial complexity and exponential, and like basically super polynomial. But polynomial means n to a fixed power, so it could mean n to the power of 5. For mesh processing, even n to the power of 2 is way too long, because you have a million triangles. A million squared is like way too long to wait for. And so a lot of this unfortunately is in the space of, well, we kind of have to build heuristics and approximations and try to figure out what works and what doesn't, but we don't really know what the optimum looks like. All right. So so this is the context behind a lot of this.
Okay. So not the startup of the application, but like a separate process preparing the asset.
I should mention, so when you're in development of the game, it could make sense to bundle, sort of for simplicity, the setup that I described, where there's a separate processing pipeline. It's very common in game engine world, but the common a way you could do this is you could also, code is code, like it doesn't really matter where you run it. You could run it inside the engine process. So if you really want to, which is completely fine, some engines do this, while in development inside your engine process, you could have code that says, oh, I have this file has a runtime ready representation, but the file has changed since the runtime ready representation was updated. So let me rebuild it, save it back to disk, and then when you ship your engine, you take out the portion that like did the whole kind of baking on the fly part, right? And your users never run it. So like if you want to run it inside the engine, that's completely fine too. And again, a lot of the algorithms are like fast enough so that practically speaking, it's not that big of a deal to run them. But the intent certainly is this is kind of, a lot of this is offline processing.
So now dive a little bit into the algorithms that actually happen in these steps. And the context for this is that we have like a huge buffer where we have the data from vertices. We have an index buffer that points into the vertex buffer, basically saying, hey, here are the triangles, right, laid out. And you have outlined a couple of steps. And the first one is indexing and kind of reaming what we have in the index buffer. So how does it work?
So the context here, so this is fairly basic, and the context here is, so I had this cube example earlier. You can think of a cube as it has 36 vertices because every triangle has 2. You can think of it as it has 24 vertices because that's the minimum that you need to represent the normals. If you removed all of the attributes from the cube, like normals and texture coordinates and stuff, then the minimum number of vertices would be 8 because you just need 1 for each corner. You just need a position. When you start from the modeled meshes, like the meshes that come from Blender or whatever, they usually have a different model of how they represent the mesh internally. For example, it's common in modeling applications to have, they don't really think about this as vertex buffer and index buffer because they're not really meant for sort of GPU accelerated rendering. It's common to say, oh, I have positions in my vertex data, but I also have attributes that are attached to like triangle corners. And so you have a triangle, or even they usually don't even use triangles. But in terms of triangles, you could have a triangle, and a triangle has each corner references a position, but it also may reference like a texture coordinate by a different index. And so there's not really this model doesn't map cleanly, right? And because this model doesn't to the GPU world, and because of this model doesn't map cleanly to the GPU world, the first thing you need to do is you need to build an actually unique index buffer where every vertex in your vertex buffer, where again, a vertex is the composition of all of the attributes that you have, is only referenced once. So yeah, so the first step usually in the pipeline is re-indexing because your source index data is usually either not existent because your source model didn't really have one, or if you have a GLTF file has an index buffer, but many exporters that save the GLTF file would not produce an index buffer rather, they would often produce a vertex buffer that has duplicates, just because kind of the way their data that this stuff comes out of had duplicates because of, these complicated sort of modeling data structures, and they just didn't deduplicate it, right? So the first thing that you usually do is reindexing, which is basically a deduplication, and all it does is it finds the unique vertices in your vertex data, and then renumbers. So it builds a view into your original vertex buffer where only unique vertices are referenced, and then uses that view, which is like a remap table, to remap both the vertex data and the index data so that you don't have use the duplicate data. This is just like a hash table, and if you really wanted to write this code yourself, it's not very hard to write this code yourself. It's a hash table, you write a hash function and stuff like this. There's 2 reasons. So some algorithms that is meshoptimizer are like this, where the algorithm itself is very, very simple. It's a hash table. It's like find unique elements in the sequence. Not a big deal. The problem is a high performance hash table it takes some effort to build, and it's not really readily available. If you write code in C++, C++ now has had for 15 years now a built-in hash table. It's really bad in terms of the performance that it takes to run it because it does an allocation per element, and it uses like often uses inefficient code to index it and stuff like this. So if you just took this code and just built it yourself in C++, it would be slow. Now, again, you may not care if you're fine with taking your mesh, taking 1 minute to process. I do care. And so because I do care, right, there's a single function in meshoptimizer that does the right thing for you on the high level, so you don't have to think about what it does internally. 2, does it as quickly as sort of humanly possible, right? There's like a hash function, there's a carefully optimized sort of layout of the, it's an array, but a layout of the internal sort of hash data, stuff like this, right? There's some caveats around if your source data is floating point, it's actually not trivial to build it's not hard, but like there's a lot of nuance here, right? So you have a floating point value. You need to compute a hash of it. Again, C++ has a function for it out of the box. It has like stdhash, I think, specialization for floats. It's really slow because it does, but it's correct at least, because it does like a decomposition, I think, of the floating point value and stuff. You can be tempted to say, well, the floating point is just 32 bits. Let me just take these 32 bits and hash them however I would hash an integer. The problem is in floating point, positive 0 and negative 0 are two distinct bit patterns because their sign bit is redundant, but they are equal. Is it a huge problem if you're building a hash function that positive 0 and negative 0 would hash to different number? Maybe not, but like it's a problem, right? So anyway, there's like a lot of weird complications around some of this, but the big reason why meshoptimizer even does this, the big two reasons are A, to have a complete pipeline that can be built out of meshopt functions, and 2, just performance of hash table lookups. But yeah, so the reindexing stuff is actually fairly simple. The difficult stuff is what happens after, right? Because the difficult stuff that happens after is, for example, the vertex cache.
Yeah. So
and this
we
is
started
where
with we started with the vertex buffer and buffer, and now we kind of gave them to meshoptimizer, and we got back either a table or already the changed vertex buffer and index buffer, like the deduplicate. And now we enter like a second part, which is vertex cache. And now can you do like a bit of an intro for how vertex cache works for you, and how do you want to like optimize it?
Yeah, so this is where we get into so the reindexing is straightforward. You know, if I just told you, oh, your vertex buffer may have duplicates, you're like, oh yeah, that's fine, I'll just filter them out. But there is this large class of problems that I mentioned in the beginning where people just sort of don't realize they might have, right? And the vertex cache is one of them. So if we think about the GPU execution model, or the GPU, I guess, pipeline model, the way it's like documented, you know, there's your index buffer, there's potentially vertex buffers, or you may even potentially render without them, and then you submit a draw call, and then your vertex shader magically gets executed with indices out of your index buffer, and then these indices get the vertex data from the vertex buffer, and then your vertex shader does, you know, beautiful computations, and then creates data that then gets fed into the rasterizer. So this is a cool model that is conceptually very simple and beautiful, but there's a lot unsaid about that model, sort of, and there's a lot of space for different GPUs to do different things with the data. So the first problem is very simple. It goes like this. So I was talking about a cube. A cube is a complicated example because it's a small mesh. It has very few of like everything, and so it doesn't translate into meaningful metrics. So here's a couple of just baseline. There is like Euler theorem or equation or whatever it's called, and there's some things that are derived from this. But okay, so like if you have an infinite plane, which if you have a very large mesh, it may be reasonable to think of a very large mesh as an infinite plane. Then this infinite plane has half as many vertices as there are triangles. Generally in an optimal mesh, in a mesh that's very smooth, that has lots of like this highly tessellated surfaces and stuff like this, you'd expect around half as many triangles as you'd have vertices. Now, this is not true of a cube. This is not true of many complex faceted meshes, but you know, there's about half. So then I give you the index buffer. The index buffer has 2x the number of vertices approximately, but this means it has 6 times the number of indices because there's 3 indices per triangle. So you give a GPU 6 times as many indices as you have vertices. Again, very approximate for many meshes. This is not like this, it's fine. A GPU could do many things. One thing it could do is it could take every triangle, it could take every vertex in that triangle, run the vertex shader for that vertex, and then you would have your 3 output like sets of data for the rasterizer to take in. This is up to 6 times slower than processing every vertex in the original vertex buffer once. You could take the entire vertex buffer, in theory, and run the vertex shader on every individual vertex, just completely ignoring the indices. Save the result of this somewhere to a GPU memory. and then take your index buffer and just, find things in the resulting buffer by index. The problem is this doesn't really conform to the model. If I give you an index buffer that references vertices 1, 2, and 7, you're not supposed to run my vertex shader on the index number 6.
Yeah.
Spoiler alert, there are some mobile GPUs that misunderstood the assignment and actually do the thing that I just said, where they take the entire vertex buffer, even the vertices that you're not referencing, they run the vertex shader, they save it to temporary memory. The other problem there is how much memory do you need? The answer is way too much, because GPUs have this complicated tension between being a parallel machine and being sort of an efficient machine. The optimal thing, always the optimal thing for parallel processing, is to process every single element independently, which means you have to have memory for every single input and every single output, all resident at once somewhere. And so in this case, it's like, oh, you have 1 million vertices in your mesh. Well, we need space for 1 million copies of the output vertex data, which is very bad, because your vertex shader outputs, conceptually it outputs floats, there is no bitpack in there, and it outputs many of them, because it's like however many attributes you're exporting from your vertex shader that are then read from the fragment shader. So so there's some mobile GPUs that kind of approach this horrible, like, you should never build hardware like this, but fortunately many of them are very old. The desktop version used to be, so the canonical understanding of reasonably efficient model of how to do this involves something called the vertex cache. So the model there is very, very simple. So I just told you, you have an index buffer that's fairly large, and it references a number of vertices that's fairly small, but you kind of don't really have space for the whole thing. So what if there was a small cache? Let's say there was a small cache for, like, 32 vertices. And what we would store in this cache is the result of the vertex shader invocation. And the key for that cache would be just the index value. So the GPU would process the index buffer. It would say, okay, there's 3 vertices, 3 index values for the triangle. Let me just look up every one of them in the cache. The cache either stores the data or it doesn't have it yet. If it doesn't have it yet, I will run the vertex shader. I will get the new data and put this in the cache. And then the cache is fixed size. And so if the cache is small, but the indices in the source index buffer are still coherent in the sense that they're like local, you're likely to see if you're ever going to see the index again, you're going to see it soon after the last time you saw it, right? Then you're fine. And this is kind of how CPU caches work. If you have a CPU cache and you have the same address and you access the same address sort of soon after you have already accessed it, it's probably going to be there. But if you run a whole bunch of extra code that pollutes the cache with a whole bunch of other stuff and then access the address again, then it probably won't have it. Now, GPUs actually don't work like this because the model that I described is sequential. You take the indices from the index buffer, you look in the cache, if the cache doesn't have them, you compute the vertex data, you put this in the cache. But this is a problem because GPUs want to process like thousands of vertices at once. So the real hardware is complicated. The real hardware is complicated and also it's not documented in the sense that, so people have reverse engineered, there's ways for you to reverse engineer the behavior of an individual GPU because there's some side effects from the vertex shader that you can observe. A vertex shader can write to buffers since DirectX 10, I think. And the model, the documentation for the API says basically, we will not tell you how many times a given vertex shader runs for a given index. It could be once, it could be many times, we will not tell you. And if you do anything in your vertex shader that would break this illusion of the vertex shader just running for individual indices that are referenced, it's kind of on you, like, it's your problem. Some different drivers do different things around this and stuff like this, but generally speaking, there are some ways to reverse engineer the behavior of the hardware here. But counterintuitively, for the optimization of this, it helps you less than you think to have the precise model of the hardware. Because of the earlier problem that I mentioned, we don't know how to build optimal solutions. We don't know how to build them quickly, but we also just don't know. Even if you have the precise way to model the behavior of this cache. And by the way, so if people who are into if people who work at like AMD or NVIDIA are going to watch this, they're going to be offended because the cache doesn't really exist in these GPUs per se. The cache is, as I said, so like the cache makes sense if you have a sequential model of execution. It makes sense as an analogy. It breaks down when you say, oh, the GPU actually processes thousands of processes at once. How does this work? The answer to how this works in some GPUs is, roughly speaking, let's say I gave you an index buffer. Let's say you looked at a small slice of this index buffer, like, I don't know, like 120 triangles or whatever. Let's say you take these index data and then just found duplicates within that batch. You would have the index value like 13 that's used like 5 times for some reason, and the index value like 17 would be only used once. So then out of this, you could build a smaller subset of the vertices that are actually used, and then ask the GPU, can you shade all of these? Ignore everything that happened before or after. Like if inside this chunk of the index data there is a value 17, that's only happened once. But in the next chunk, it's going to happen 3 times. It's fine. We will process it again. We are trying to be parallel, which means we can't take the full advantage of the kind of sequential reuse. So you take all of this batch, you kind of compact this batch by removing the duplicates from it, and then you send the whole thing to the Vertex shader execution, and then the rasterizer has to pick up the pieces and kind of reassemble things back from the data that the Vertex shaders processed. But it kind of doesn't matter again, because so the interesting fundamental property of this is actually just if your index buffer is optimized for locality, meaning if you have seen an index once, if you're ever going to see it again, it should happen soon. How soon is hard to answer, but it happens soon. And so meshoptimizer has a function to go all the way back, which basically does this optimization. It's based on an algorithm that was invented by Tom Forsyth way back, I forget, like many years ago. The interesting thing about that algorithm is it's driven by a lot of heuristics, or by a few heuristics. So it looks at a few, it kind of models a cache, but it doesn't model it very precisely, and it doesn't use a specific replacement policy. Like it doesn't have this notion that, a cache is 16 vertices, and we are seeing the vertex that is not in the cache, which means the last vertex that was there should be removed. This is not kind of how it works. It uses heuristics. So I use an algorithm that's based on this. I did an interesting thing many years ago, which is this. So if you have an algorithm that's driven by heuristics, it's difficult to tweak these heuristics. You have, in that algorithm, you have a bunch of like numbers that are saying, oh, if like the vertex is going to be referenced again by like 3 triangles, this is what the score of that vertex should be, and this is how we should model the like value of replacing this vertex now versus later. And what do you set any of the numbers that guide any of your heuristics is always like an impossible question. I feel like half of the time that I spend on all of these algorithms is just like, how do I tweak all of this? So I did something pretty cool a few years ago, possibly many years ago now. I have a blog post about this. Some of the stuff that I've done for meshoptimizer has nice articles on my blog. Some is like, I don't know, 20%. One day I will get to the rest, 80%.
Zoox.io.
Zoox.io. Yes, exactly. Like and subscribe and all of this. So if you have an approximate description of how hardware works, you could take a given set of index values and you can ask approximately how many times will the vertex shader run on the whole index set. You can actually gather this data precisely if you have a GPU, because the modern graphics APIs expose what's called the pipeline counters that will tell you how many times the vertex shader has run, basically. And it's an interesting value to look at, because you can look at the mesh and it's going to be a number that is not the number of vertices, it's larger because the cache is like imperfect. But it's also not the number of indices, it's much smaller. And so like, you see the cache working pretty good. And you can also see on different GPUs it's going to be small or large. But it's expensive to, so I wanted to run an optimization algorithm that took a large collection of meshes and then had this small set of numbers that determine the heuristics, and then tweak these numbers in kind of, it's kind of similar to how neural networks are trained these days, but for neural networks you need a gradient, and you don't really have a gradient there, so it's a different method, but it doesn't matter. So like you have this small table of numbers that you're trying to optimize, right? So you take a large collection of meshes. Ideally, what you would want is you want to tweak the table, run the whole optimization process, measure the number of vertex shader invocations on all of these meshes across multiple different GPUs, and then, if it's better, then you keep the adjustment to your table. Many people did genetic algorithms, actually, I think, as part of their computer science courses in the university, and this is similar to that too. So the problem is it's too complicated to get like multiple different GPUs and actually run this code and stuff like this. So I built simplified models of how I believe GPUs work that count this number without like running the GPU, and then ran this multi-day optimization process in a large series of meshes, and then came up with like 32 numbers that are perfect. And then, I use these 32 numbers that are perfect. So there's like tricks like this that are interesting, intricate. And again, so this problem has an interesting property. You could try to get all the way to the optimal result. It's very, very hard because we don't know how. You could try to get within 1%, or you could try to say, I'm running on AMD GPU versus an NVIDIA GPU. And AMD GPUs do this way, NVIDIA GPUs do this that way. Sometimes you can get like an extra 1 or 2% out of this. On modern GPUs, so having run the optimization process at all is already so good that, the extra like small little details matter a little bit less than you would expect. They still matter, but they matter less because this is just one stage of the pipeline. And even if you have a large mesh with many vertices, it's tempting to think, what's taking time during the rendering of this mesh must be all of the vertex shader processing that's going on. It's complicated. Sometimes it is, sometimes it's not. If you haven't optimized your index buffer for vertex cache, probably your vertex shader invocations are not doing very good. But if you have optimized it, it's very, very likely that other stages of the pipeline restrict your performance in ways that kind of overshadow the extra like 1 to 2% gains that you could have from like the more optimal sequence or whatever. But yeah, so all of these problems are hard. So going all the way back, this is why Mesh Optimizer exists, right? This exists for you to not think or care about, like on NVIDIA GPU, the replacement policy is like this, and you run the function gives you an index order, and index order is reasonably optimal for a large set of GPUs. On some GPUs, it doesn't matter as much. So on GPUs that just take your entire vertex buffer and just run the vertex shader on every one of them, like it doesn't matter. They're bad in other ways, but this algorithm doesn't matter as much there. But you run it, it basically never hurts. You run it once during the mesh processing, it's fine. And then you get the final index order. And that's what you feed to your GPU, and your GPU is happy. So yeah, this is another interesting property of Mesh Optimizer, which this problem kind of exemplifies, is so you don't really know how your GPU works because the graphics vendors don't tell you. If you have like console access, then sometimes you have more in-depth information. But even then, A, it's partial, B, it's about a given model. So, for example, in game development, there is this unfortunate trend, there used to be this unfortunate trend, at least, so people would build games for consoles, build proprietary engines for consoles and stuff like this. They would get like a lot of knowledge about how the GPU in that console, which all happened to be AMD GPUs until Switch. And it's the same generation of AMD GPUs, which doesn't help. So it's like you have a single type of GPU that you have spent 5 years of your life like digging very deep and like shaving off cycles and stuff. And then you just assume everything else works like this because, this is your model of hardware now. Well, turns out like different GPUs are different. So the vendors don't tell you how they work. And if you know that the problem even exists, then you can try to figure out the properties of the problem. But sometimes you don't know. So like with this Vertex cache, right? The Vertex cache specifically is a well-researched subject because there is multiple papers written and stuff like this. But if you don't know that the order of indices in your index buffer matters, it may never occur to you to ask. Does it matter, right? And there's many cases like this where sometimes the answer is yes, sometimes the answer is no, sometimes the answer is on some GPUs it is, some on some GPUs it's not. One of the values of meshoptimizer is honestly just if you read through the entire manual, it may teach you things implicitly about the behavior of graphics cards that you didn't know existed. It's like, oh, like why does this thing exist? Well, it's because things are complicated in this way. So yeah.
Yeah.
So this is the Vertex cache.
And can you tell me, you have in meshoptimizer functions to analyze, like you, for example, to generate
right.
cache and then analyze, so get information back. How would it come from?
So this is actually directly related to the thing I just mentioned, or when I worked on this problem originally. Every time you work on these optimization problems originally, let me backtrack. If I gave you two index buffers that represent the same mesh, but had a different order, you wouldn't be able to tell the difference, right? So like, I could, if I showed you right now meshoptimizer running, you wouldn't see it other than like, I could show you an unoptimized mesh versus an optimized mesh. And for these optimizations, they don't change the rendering result, unless your rendering is like dependent on the triangle order, which it shouldn't be. So like nothing changes. So how do you know which one is better, right? And it's difficult to work on any of this type of stuff without having any metrics. So I originally built some basic versions of the code that basically looked at an index buffer and asked, okay, how expensive do we think this buffer is in the sense of how many vertex invocations do we think the sort of the GPU would do here? There's a classical metric called ACMR, average cache miss ratio, which is like number of, I think, times the vertex shader ran divided by number of triangles. It's a weird metric to think about because it divides like vertices by triangles, and it's like, who knows? There's a better one called ATVR, which is average. I don't know. The documentation has it. It's been years. But basically, you want metrics for this stuff. A lot of the work I do on meshoptimizer, at some point in this process of working, I end up having to write some code that gathers some metrics around the specific problem that I'm working on. And then because we don't know the optimum and we don't know kind of how to get there, and we deal a lot with heuristics, what I end up doing a lot is, okay, here's like a scatter plot for like my collection of like tests, like 100, well, it's more than 100, but like hundreds of meshes. Here's like 100 points on the graph, right, that measure some specific property. And I changed an algorithm as here's a different 100 points. Or here's how it changed. Like, is it better? Is it worse? Like, it's better on some meshes, it's worse on others. How do you quantify this? So when I did all of this work way back in the day, I wrote some functions to compute these efficiency properties of given buffers. You aren't really supposed to use these functions. They're not for you. They were for me. And actually, after I did this genetic algorithm type stuff I was talking about, I changed these functions to be more accurate to the behavior of the hardware, and then I use these functions to run this optimization process. But it's like, okay, so here's a random example. On an NVIDIA GPU, the Vertex shader runs 32 threads. Everything runs 32 threads, like everything runs in warps. And the model that I described earlier, where you take a slice of index data and you like compute duplicates out of this and then you give it to GPU and stuff like this. in that model, it's convenient to assume that if you have a single vertex shader warp, they're called, that runs 32 vertices, processes 32 vertices, it's convenient to assume that these numbers will not have duplicates because it processes 32 vertices, writes 32 outputs to whatever buffer it writes them to, and then the rasterizer can just take any 3 values out of this and like use it. On some older NVIDIA generations, I don't know. So there's like a paper on this. I don't remember the authors, but if you Google for like NVIDIA Vertex Cache behavior or whatever, there's a paper where people reverse engineered the specific behavior of the NVIDIA hardware of some older generation. I think it might have been GTX 1000 or something like this, or GTX 900. So like an old card, a pre-ray tracing card. And it turns out that you have this reuse, but it's limited. And I think if you have, basically out of the 32 vertices, there's some sliding window that's smaller than 32 that can be used by the rasterizer to pluck things out of the result. But if you have the vertex in the beginning of this 32 sort of thread, and at the end, a rasterizer may not be able to take both of them and use them for like rasterizing a triangle. So my point is basically, okay, the actual hardware behavior is like weird. And it's weird in different ways on different GPUs, and you don't want to know because you can't even optimize for this. There's really surprising results from this. So I think when Tom Forsyth came up with his algorithm, at the time, NVIDIA had a version of an algorithm. I think it might not have been open source. I think it might have been on consoles or something. I don't remember. And it like tried to model exactly what happens in hardware and tried to optimize things carefully for it. And like on many meshes, the heuristics algorithm did better because we don't know how to optimize. And it's very, very easy. An algorithm usually can have a very perfect local view into the problem. It's like, okay, if I assume right now the vertex cache or whatever, whatever the actual hardware state is at the point looks like this. If the next triangle we see is this is what happens. This you can model if you know exactly what the hardware does. However, if you try to build an algorithm that uses this knowledge, you end up doing local decisions. You end up being, I think I should pick this triangle next because this is what will happen. Often you end up with a local minima or maxima or whatever. So like you sort of think you optimize things, but your algorithm make decisions that looked really good at the time for the algorithm state. But if you look at the result, actually the traversal is suboptimal in some way, and it's hard to know. So this is like just a generally difficult property, and this is why it's very difficult, even if you have the precise model, to optimize. And so, you can you can convince yourself that you can do much better because you know the exact specifics, but then you try to build an algorithm based on these specifics, and sometimes it's not better. So it's a complicated space. But yeah, the good news is that, the model that I will get to mesh shaders at some point, but so the model that I described is interesting. All of the vertex hash and index buffer optimization, stuff like this. It's interesting because it's the one thing until mesh shaders that has survived. For many, I was trying to remember before our conversation when index buffer appeared in earnest. I don't remember, I don't know, but like I know I used them in DirectV 7. I think they may have been there in DirectV 5, I'm not sure. This is the thing that goes back like decades before GPUs got shaders. Vertex caches existed. And so the fact that today there's behavior that resembles a vertex cache, it's not a vertex cache, but resembles a vertex cache, that has persisted through, it's like many versions of DirectX and vertex shaders and programmability and compute shaders and all of this is kind of like fascinating. But fortunately, whenever you use mesh shaders, you don't have to think about the vertex cache.
Right now, we're not even in the mesh. By the way, I'm looking at like how many things are there on the list to talk about, and like maybe we are actually going for
the good news is we talked about the most complicated topic out of the traditional rendering pipeline. I think everything else we can breeze through.
Okay. So in the traditional rendering pipeline, with indexing and remapping, then now Vertex cache, and then next on the list is overdraw optimization. Can you highlight how this works?
Let me super briefly talk about overdraw and then a couple other things. Just because I think they're less relevant, less interesting, and stuff like this. But so let's talk about overdraw briefly. So the overdraw optimization is one of the things where I think in my documentation I say, oh, like it's optional. You may do this, you may not do this,
Yes.
and it's a thing that used to be more important, and it kind of stopped being important like many years ago, depending on the renderer that you write. This is again going back to, okay, it's like a collection of tools. Sometimes the tool is useful for you, sometimes the tool is not. So if you render a mesh and the mesh has triangles that are arranged in the order such that you're likely to see a triangle, so if you have a triangle that's like further away, you're going to render that, and then you're going to render a triangle that's closer. The GPU will generally respect the order that you have put the triangles in. And so it won't render them literally in sequence because it's a parallel beast, but it will preserve the order usually. And so what this means is that if you have the triangles kind of arranged in this way, then you may shade the pixel that these triangles cover twice. Now the caveat is probably you have depth prepass, and if you have a depth prepass, you will process a pixel twice, but you will process it inside the depth prepass where it just writes depth, and that's fairly cheap. And then after this, so like the cost that you will pay for triangle overdraw is actually fairly small. And then in some renders you don't have depth prepass, like it happens. So there is some renders where you don't really have a depth prepass, or depth prepass is only used on some geometry. And then if you render, overdraw is a scene-specific property, really. Like you can't optimize a mesh for overdraw, because what if I render 5 meshes and they're like structured in a way that one occludes the other? And even if you render a mesh, I can render it from like multiple different angles, and in one angle the triangle order is this way, and in one angle triangle order is that way. If you have a mesh that is convex, so if you have a cube, it actually doesn't matter what order you draw triangles of the cube, the overdraw is going to be 0, because usually you have backface culling, and so a cube would have like 3 of its faces, or sort of 6 of its triangles like facing camera, and then 6 back-facing. The back-facing ones are going to be culled, and then the front-facing ones are going to not cover each other because they're all, they're disjoint. So if you have a convex mesh, generally speaking, your overdraw is 0. But you can have weird meshes that have weird structure. So, okay, let's say you have a house, and the house has chairs inside it. And it so happened that it's all part of the same mesh because you're very draw call conscious, you merge everything together, all of your textures is one thing, etc. And so you have chairs inside the house. And you're rendering the house, and if you render the chairs first and then the walls of the house last, then you're going to process the pixels of the chairs twice. And if you're going to render the walls first, then when you process the pixels of the chairs, they're going to be rejected by the depth test and not result in any fragment work. And so I have an algorithm that heuristically optimizes this kind of inside-out order, where if you have a complex layered mesh, the parts that are inside should go after the parts that are outside in the index order, so that they're rendered after this. And this is a property that's invariant to the view direction, because if you like the chairs inside the house, regardless of the direction that you look at the house from. But again, it's not and there's like reasons for why the library has this algorithm. It's like occasionally useful, but it's not part of the default. So when you're building a pipeline, you have to run reindexing because your index buffer is probably terrible. You have to run the vertex cache optimization because like otherwise it's just like there's no reason not to, and otherwise you just are gonna see performance impact on some GPUs. You don't really have to run the overdraw. Overdraw is like, okay, in some specific cases it helps, but like it's not a generally necessary thing to do these days. And then you usually have to do the vertex fetch, and then you usually have to quantize the vertices, but like all of the other stuff is not super necessary. Let's actually let's ignore vertex fetch because it's not super interesting. It's like you just have to run it as a function call. It's fine. Let me briefly talk about vertex quantization to just conclude the rendering pipeline so that we can get to other like interesting things. Because so you have to realize all of this existed in the library from its first years, and the library was created in 2017. So it's been 9 years, and
I think.
so like I think last year I wrote. I think in the release announcement last year I wrote 99 and a bit years or something like this. So basically, it's almost been a decade, not quite, thankfully, and a lot of the traditional algorithms have really solidified in the first few years, right? Because this is the first thing you work on. But this is like kind of distant history for me at this point. So let's just briefly talk about the vertex quantization, because this is this example of you should read meshoptimizer documentation because it will tell you to do a thing, but it will not really do a thing for you. You should just do a thing. And this is this is going back to this, how do you represent the vertex components question. So when you run your vertex shader, the vertex shader has to read data from the vertex buffer. Sometimes this read happens automatically because you use like an API that forces you to bind the vertex buffers, and your vertex shader just declares inputs. Sometimes you can do this, and you often should do this now manually, like your vertex shader gets an index from an index buffer, and then it can just read the data indexed by that index from whatever buffers you like in whatever, however you like them to be structured. But the general idea is very simple. If you have less data that you read from memory in the vertex shader, things are going to be better. It's very straightforward. Things are going to be better for two reasons. One is you'll just spend less GPU memory on this. And GPU memory is also an important optimization kind of target for meshoptimizer because, memory is expensive these days. The other benefit, of course, is that these reads will come out of memory, and then they go through a cache, which is like a traditional CPU style cache, I would say, like an L1 cache or L2 cache. They go through a cache if data that's referenced by the vertices is not in the cache. There's a cache miss, and the GPU has to do some other work while it happens. And the less data you read, kind of the less data you'll have to read from memory, which will reduce the time that your shaders spend like not actually doing useful work and all of that stuff. So generally, you should just prefer compact data, right? And this is a property where, we talked about vertex cache. The property of the vertex cache optimization that's useful is you do this, you don't think about this, it doesn't change your rendering result, it just makes things faster. If I gave you a float, you can't remove the information from a float without affecting the rendering result. Sometimes the result will not be affected significantly. Maybe the pixels are identical because you moved the float by like an epsilon and it turned out it didn't matter. But maybe it did matter. Maybe you introduced a small gap by moving a vertex, or maybe you were trying to remove so many bits from a value that the results did change, right? So there is a series of trade-offs that you make in your processing pipeline that are potentially affecting the rendering result. And when you make them, you have to figure out, it's like, okay, for example, when I'm storing normals. So it's a bad idea to store normals as 3 32-bit floating point values, like a terrible idea. It's also a terrible idea to store them as 3 half precision values, although it's half as terrible, I guess, but it's still bad. There's optimal ways to store a normal that involve using octahedral encoding, or there's a few different encodings that people come up with. But how many bits do you dedicate to each encoding? Which encoding do you use? Because there's not one, there's like 3 or 4, right? And all of that depends on your application. So normals are a good example where if you are just doing diffuse shading, the normals are very resistant to kind of removing information from them. You can store a normal in like, 10 bits for the entire vector probably, or something like this, 12 bits for sure, and not see results in diffuse. But once you do specular, it's very, very easy to see quantization artifacts in specular if you quantize the normals, if your mesh was high density, because sort of you removed enough information from your normal vectors, which displaces them, which rotates them kind of in different orders, and you could see artifacts, right? So it's kind of similar, I guess, when you store images in JPEG, right? You can select the quality. And the lower you go in quality, the more quantized the underlying representation is. And the further you go, the more blocks you see. And sometimes like on some images it may not matter, but on some images it does, right? So you have to quantize the vertex data, but how you quantize the vertex data is very, very dependent on the application, right? So meshoptimizer has a couple of helper functions, really, just because. So when you take a float and you want to store, let's say you have a float, let's say the float is from -1 to 1, which, normal components are. And let's say you want to store a float like this in a byte. There's a very basic, very classical representation that's hardware supported by like directory, 10, etc. That's called snorm, signed normalized. It's basically you just store an integer, and an integer has an uneven minimum maximum. So like if you have a byte, the maximum byte value, the maximum signed integer value in a byte is 127, and the minimum is -128. It's asymmetric. For normals, it's really, really bad to do asymmetric ranges because you want to represent 0 exactly, and you want to represent 1 and -1 exactly. Otherwise, things break down in weird ways. So the representation is very simple. It just says 127 maps to 1.0, -127 maps to -1.0. We ignore -128. We lose like one value out of the representative values of the byte. 0 maps to 0, and then there's just like a linear range there. If you take a float to convert this to this range, it's very simple. It's a few math ops, but you have to round correctly. If you have the value that's like, closer to like -37 than to -38, you should use -37. And people who do this, it's very, very easy to write this by hand and mess it up. And when you mess it up, your precision drops, your error basically goes 2x because you didn't do your rounding correctly. And because of this, meshoptimizer provides this function, not because it's like very difficult to write, but because it's an example of the function, it's written correctly, and if you use it, you don't have to think about this, right? But otherwise, Vertex Quantization is kind of up to the application, and the reason why meshoptimizer documentation even mentions it is not, it's like, oh, this is a thing that meshoptimizer solves for you. It's like, this is a problem that you have, and you should figure out what you're going to do about this problem, right? But it's you're on your own. Right. But yeah, so the minimum pipeline is basically reindex, optimize for vertex cache, optimize for vertex fetch. We skip this one. It's like, go read the docs. I just don't want to take too much time on this, but it's a very basic important step. And then you do vertex quantization. And then there's some stuff that you can do on top, but this is kind of the minimum bar. If your engine uses meshoptimizer, it probably does these things. If your engine doesn't use meshoptimizer, shame. But at least you should do these optimizations. If you are not using meshoptimizer and are not doing this optimization, then that's like pretty bad. Although again, it's complicated because if you only ever run on Apple GPUs because you're building an iOS only game for some reason, then some classes of GPUs have like sufficiently weird behavior that the degree to which different optimizations affect different GPUs matter in different kind of aspects. The vertex cache matters like fairly like to a large degree on modern desktop GPUs to this day. The vertex fetch that we did not talk about doesn't matter as much, but there are some mobile GPUs. So there are mobile GPUs that I mentioned in the beginning that shade your entire vertex buffer. I actually lied a little bit. It's not your entire buffer. It's the range between the minimum index value and the maximum index value. So if your index buffer has indices 1 and 1000, and it's just two indices, let's say it's a triangle, so it's 3 indices, whatever, 1, 2, and 1000. it's going to shade like 1,000 vertices. So some older mobile GPUs do this. And Vertex cache optimization doesn't fix this because it just reorders things. Sometimes you can be in a position where you have like really suboptimal index data like this. And so when you use meshopt functions, like you don't have this because everything is like tightly packed and stuff after the result, after the end. But there's like specific cases where you can look at this and you can be like, oh, I used the Vertex cache optimization and it didn't save me anything, so I guess I don't need it. And the problem there is A, on some GPUs it may be way more necessary than on others. B, it may not be needed because you tested it in such a scenario that doesn't care. Like if you're rendering 1,000,000 cubes, you don't really optimize a single cube for a Vertex cache. It's so small, there's so many vertices there that it doesn't really matter which order your triangles are in, like it's fine. And so in that scenario, like you don't care, but then you start rendering meshes that are very complicated and you forget about the fact that you haven't really done due diligence on your pipeline, and then this is when it starts to matter. So, but use mesh, it's going to be fine.
You mentioned a shame if you don't use meshoptimizer. We didn't talk about this, but meshoptimizer is open source with MIT license. I want to come back to this at the end generally, but like if you want to use meshoptimizer, it's right there. It's in the open. You can do it. Yes. There's nothing stopping you from using it.
This is not a sponsored episode because there is nothing to sponsor.
On the Vertex Quantization, last question to sort of wrap it up. It introduces the artifacts, and so far we were kind of like, you just can do it and like don't worry, just call the function, that's it. How would you test it? Imagine like, you already have a scene, you're building the next Witcher game, and like we are now include meshoptimizer. So how do we want to now go through all the assets and see what are the behaviors or what are the like artifacts? Like how do you want to do it?
Yeah, so for quantization, there's a couple of different ways to do this. The industry approach is like, usually to just test it, I guess. There's some things that if you've built pipelines before like this, you just sort of expect that some things will work and some things will not work. And it also depends a little bit on the types of the mesh, types of the geometry. So I guess maybe just a couple quick things. So one is when people quantize Vertex data, it's very convenient to use half precision floats because it's just like there, it's fine. Half precision floats have around 11-bit effective precision on a given interval. Like if I told you a mesh is like 3 meters, and so the vertex coordinates are from like 0 to 3, then on that entire range you get around 11 bits of effective precision per component because it's like a 10-bit mantissa plus an implicit 1-bit. What production renderers usually do is they would usually use integer quantization, because you could have the same 16 bits that a half precision float is, and then you can take the bounding box of the mesh, and then you can rescale the vertices to go from 1 to 0 within that bounding box, and then you can use the integer quantization that I was talking about, and then gives you sort of the full 16 bits of precision. So there's things like this that are different in different representations. And also there's going to be some meshes where, for example, positions cannot really be quantized without a very apparent loss of precision, of like visual fidelity. Things like this get more interesting, I would say, in mesh shading, because there you have more options that are available for you. But I think what I've seen in production pipelines often is, for example, by default, you enable quantization. Normals are an example of a component that you can quantize to a fixed number of bits. So I mentioned like 12 bits for the whole vector, which is too small. But normals you can usually quantize to like, I'd say like 20 something bits for a normal if you use octahedral quantization, etc. is going to be a thing that you can just enable and just never think about because it's going to be fine. Some production renderers use like 24 bits. I think some use like 20. So there's somewhere in that range is going to be a value that's basically you're never going to hear from an artist again. Positions and texture coordinates are going to be examples of things where you will hear from artists again. So what I have seen, for example, in production pipelines is either we look at the extents of the mesh and we say, oh, this is too large, so we think the apparent error will be too large, so we are not going to quantize. Or we are going to quantize everything, and then artists will occasionally come to us and be like, oh, this mesh looks terrible, and there's a checkbox for them to check to like disable that. Or I think Unreal does this, maybe, but maybe not, I'm not sure. If you're building a complex game, it's very, very handy to give your artists basic classification. So like this is a small prop. So like a small mesh, like a I know I'm looking at my desk, it's like a mouse or a keyboard. I guess you wouldn't have a lot of these in a game, but or like it's a large prop, or it's a character, or it's a piece of an environment, or it's vegetation. So give them like 10 categories, and then usually within the category, it's a binary decision. It's like, oh, small props are fine, large props, I don't know, like characters, maybe you quantize with like more precision. But there's multiple different things you can do there. I think the critical property there is like to think about this problem and think about what would make sense and then test a couple options and then kind of ship something. But I think this is one of the reasons why if you look at Unity, I believe Unity spent like a long time not doing vertex quantization at all, like anywhere in their import pipeline, which is like very, very inefficient. But I think for them, they didn't really want to build presumably, I don't know, I never worked there, but presumably they didn't want to build like complex heuristics to figure out if it's fine or not. And because it's a general purpose engine, you don't have an option of artists going to like, Unity people and asking what's up. So maybe they just didn't want the complications associated with this. But again, so even if you only quantize the basic vertex format, the most basic thing if you have a PBR pipeline is a position, vertex position, texture coordinate, normal vector, and tangent vector. Sometimes you don't have tangents, sometimes you have other stuff, it's complicated. Even if you just take this, so let's do the math. Positions are 3 floats, normals are 3 floats, texture coordinates are 2 floats, and then tangents are usually 4 floats because there is a vector and there's like a winding component. So that is, I was not actually doing the math, I think there's 14 floats. Even if you ignore position and texture coordinate that are sensitive to quantization errors, even if you completely ignore them and then still store them as floats, you can still take the other half of the vertex and compress it like 4 times by doing quantization with like fairly small bit count, because for all of the vectors, directional vectors, the default 32-bit is just crazily excessive. So even just this is a safe choice that basically any engine can make. And even though it's not optimal, you can get more, but even just that is so much better than doing nothing. And I think Unity didn't really do that, but I'm sure by now they do. Any production engine, I would say, at least does vertex quantization, because this is a thing where this is a widely known thing that you can do and should do.
Okay.
Some of the other stuff is less widely known.
Okay, so this wraps up the rendering pipeline. We went through indexing, vertex cache optimization. We kind of skipped fetch and then vertex quantization. And there are a couple of actions that you can everybody can read on the meshoptimizer docs, which, by the way, crazy good resource to even learn what is actually happening in between the lines. Really good, like on point, like very technical, straight, direct. I really love it. Now we move forward. Do we move to mesh shading?
Let's talk a little bit about mesh shading. Just as a, I won't go too much in depth on this, I guess, just to be conscious of time. But the pipeline that we've been talking about with like vertex shaders and index buffer and stuff like this, so it still exists. It's still relevant. It's still what you'd see probably 90% of the game engines use for like most of their content. So there is a new way to, the way this pipeline is structured is literally around this idea of what is, how do we know when we need to run the vertex shader? And there is this abstraction, which is the index buffer that sometimes spawns vertex shaders. We won't tell you how much, how often. So when compute shaders got introduced in DirectX 10, before this, all of the shaders kind of told you that they are doing things one element at a time, but just in parallel, and you didn't really have visibility into what happens under the hood. I think compute shaders were the first case where, so when you run a compute shader, it's just general processing, but it's not general processing one element at a time. It's a processing one group of elements at a time. You say how big the group is, and so you say, oh, I want to process things in groups of, like, let's say 64 elements. And I know my function is going to be run 64 times for each element inside the group, but the different invocations inside the group kind of happen together, sort of in lockstep, not quite in lockstep, dependent on hardware, but, and we will even give you special APIs, in compute shaders case, it's shared memory, that allow different threads to talk to each other. This API, I guess, got refined later with like other features, but mesh shaders represent a similar shift where sort of it's a different way to think about the pipeline that goes on before rasterization. We did not talk about, and we will not talk about, all of the other horrible shader stages that happened before the rasterization, because like, oh, isn't there like tessellation, evaluation shader, and geometry shader, and tessellation control shader, and I don't know, maybe there's more that I'm forgetting right now, but like, so if you look at the entire pipeline diagram in Direct Redux, it's like complicated, there's like many things. And this is a representation of the industry spending many years kind of experimenting with ideas and shipping some of these ideas, and then learning that some of these ideas don't work super well. So geometry shaders were like this, where people thought geometry shaders were awesome for a whole bunch of reasons, and then it turned out they are not efficient from the hardware perspective, and so they're still there, because you can't unship a feature once you ship it, but...
Welcome to hardware.
So mesh shaders are another attempt, or an attempt, to basically rethink that entire pipeline, right? So there's like vertex shaders and tessellation evaluation shaders and geometry shaders. So what if none of this stuff existed and you only had one stage? There's task shaders, but let's ignore this for now. The only really important one is mesh shaders. So what if there was one stage that took actually the thing that I was talking about earlier, where one way that GPUs could implement the current model is by looking at a slice of the index data and then kind of deduplicating this, coming up with like a bunch of things, doing vertex shading on that batch like at once, and then giving the whole batch of results to the rasterizer, and then having the rasterizer work with that. Mesh shaders are an attempt to do that, but sort of expose this directly to the user in a way that the user can understand and reason about and control on the programmatic level. So forget everything that you know about like existing shader stages and index buffers and everything. What you get instead is you get a shader stage, one shader stage that runs before the rasterization pipeline, and its job is to give triangles to the rasterizer. How does it do this? Well, you know, it would be inefficient to give a triangle 3 vertices at a time. So the way you give it to rasterizer is you give it a bunch of vertices, and then a bunch of triangles that reference these vertices. So it's kind of like a micro mesh. There's a vertex buffer and an index buffer, but the number of vertices is small. And you directly tell the rasterizer the maximum amount there when you like build the shaders and stuff. So let's say you have up to 64 vertices, and then let's say you have up to 100 triangles. I will not go into the exact numbers because you know this podcast will go for too many hours then. Then because you only have 64 vertices, your index data could actually be 1 byte per index instead of 16-bit or 32-bit. You just need 1 byte, 8-bit. And this is what your mesh shader outputs to the rasterizer. And when the mesh shader runs, instead of running like a vertex shader where it processes like one triangle at a time or one vertex at a time, it kind of processes the whole batch of all of the vertices and all of the triangles in one compute-like shader invocation. And it's up to you, so it runs multiple threads. You tell the GPU how many threads you want to run, and then it's up to you as to what to do. For example, you could say, oh, I have 64 vertices, but I'm only going to have 32 threads in my invocation. And this is how the NVIDIA's original extension for this worked, because NVIDIA sort of pioneered the extension work there, at least. And because I have 64 vertices and somebody needs to transform them, but I have 32 threads, I'm just going to take every thread and then process 2 vertices. Because there's a total of 64, right? And then you need to output triangles, and there's up to 100 triangles, so maybe I will take every thread and have it process up to 3 triangles. And when we say process, the most basic shape is just give the rasterizer the 8-bit index data. There's complex stuff you can do in mesh shaders. So for example, you can do culling, you can do geometry synthesis, like you can say, oh, I'm going to render a bunch of cubes. And you can represent each cube with, let's say the cubes are Minecraft style cubes, so they aren't even rotated. So then you can represent each cube with like a center, and that's it. I don't know what else you need, like some texture coordinating, like a material, right? So a mesh shader could literally take a chunk of voxel data and then just generate like a cube from it, because you're limited in the amount of output data inside one mesh shader invocation. You have to think about how you do this. It's like, okay, a cube has 12 triangles, we can output up to like 128, so I guess it's 10 cubes per mesh shader invocation, stuff like this, right? So you have to think about this, you have to budget things, and also the real hardware works in surprising ways sometimes around mesh shaders, as it usually does. So there's some performance things that are very non-obvious, but the basic idea is the mesh shader gets like a bunch of index data, passes it to rasterizer, gets a bunch of vertices, transforms all of the vertices. There is no vertex shader in this model. So the mesh shader literally outputs data to the rasterizer, which means the rasterizer never cares about the world space position of your vertices. It only cares about the clip space, the post-transformed projected data. Now, so that's cool. How do you get the data that you're going to give the rasterizer? You have to do 2 things. You have to split your mesh into these small chunks. They're called meshlets, usually. Sometimes they're called clusters, but this term predates mesh shading. So I like the term meshlet when referring to the sort of mesh shading specific stuff. So you have to take your mesh, you have to cut it into these tiny blocks of data. For every block, you have to have a bunch of vertex data. You have to have a bunch of triangle indices that are indexing like inside this buffer. So your first problem is you need to cut the mesh into pieces, right? And so this is already a difficult problem. Like, how do you do this? It's not super clear. It's not super clear primarily because sort of how you do, there's many different ways how you could imagine cutting a mesh into like units of like 64 triangles, right? And going back to our earlier conversation, some of them are efficient, some of them aren't, some of them are efficient on this hardware, some of them aren't. I'd say this is a developing space because NVIDIA was the first to ship mesh shader support in their like ray tracing capable GPUs. And the features are not related, but it's just they had an RTX card. The first RTX card supports ray tracing and tensor cores and mesh shaders. It was a big release. And then AMD shipped ray trace mesh shading support starting from RDNA 2 generation. So this is Radeon 6000. But there's a lot of weirdness around the hardware support in that generation. And so then when they shipped the next one, the RDNA 3, the efficiency properties changed a lot. So so there's complicated issues around kind of the efficiency in that world. Also with mesh shaders, there is this fantastic hidden property that I actually didn't learn about. So I wrote some algorithms to basically split the mesh into these clusters. We don't really have time to talk about the internals, but it's the same type of problem where it doesn't really have precise solution. You have to do heuristics. It's not super clear what you optimize for, etc. One funny thing is, so if you look at the extension specification, it just tells you here's the API, and then if you look at the NVIDIA blog post, it just tells you, split the thing into meshlets and stuff like this. And so I wrote some algorithms to do that. They got refined since. But one funny property that I accidentally learned about later was that for NVIDIA hardware, the order of the triangles inside this micro index buffer, the 8-bit index buffer, matters. You kind of give it all at once to the rasterizer, but maybe the rasterizer has some magic. This is the type of thing that the vendors don't really tell you about. So meshoptimizer has basically two functions, more than two, but it has a class of functions that gives you a bunch of meshes for your input mesh. And that's just a partitioning where for each meshlet you get like vertices and you get this micro index buffer that you can then take this data and then just directly plug into your mesh shader and then directly render this stuff on the GPU with a mesh shader extension. And now there's also a function called optimize meshlet, which takes a single meshlet and within that meshlet reorganizes the data so that it's like efficient on various hardware. I think in general, though, this is interesting because only a subset of GPUs support this. There is some efficiency consideration around is it a good idea to do in a given case? There's some complexity around if you are, God forbid, using tessellation. Mesh shaders don't support tessellation. You can implement tessellation with mesh shaders. They are powerful, but they are also constrained and complicated, and so it's difficult to do, right? And so there are some games, though, that have, one game that is known to have done this is Alan Wake 2. So Alan Wake 2 switched to using mesh shading basically in their renderer. I think they may have a fallback path for older GPUs, I'm not sure, but they have a meshlet kind of first renderer where they think about their meshes as a bunch of meshlets and then they use mesh shaders for this. They use meshoptimizer, of course, to prepare the data for mesh, of course, for the mesh shaders and stuff like this. There's reasons why you might want to do this. Meshoptimizer helps you by giving you the necessary functionality to even start, right? It doesn't tell you what to put in your mesh shaders. So there's a bunch of things that you can do in the mesh shaders that it's difficult to do in a traditional pipeline. For example, you can do additional forms of culling that Meshoptimizer does help you a little bit with. So one intuition, so we talked a little bit about the overdraw. Let's take a different example. So let's say I have a big sphere, or it could be a big character mesh to make it less abstract. Let's have a character mesh, and you cut the mesh, and it has many thousands of triangles. And then you cut the mesh into these patches, meshlets. Every meshlet is compact. It's in the same place on the mesh usually. It makes no sense to take a bunch of triangles from different places in the mesh. It's much more better if things are local. In a given character, there's going to be a lot of meshlets that are facing away from the camera in their entirety, like they're on a backside of the character that you don't see. Traditional rasterization pipeline involves taking every triangle, running vertex shaders even for the vertices that are part of the triangles that you never see, because you don't know if a triangle is going to be seen until you process all three vertices, so you have to have done all the work. And then submitting all of this to rasterize, and the rasterizer looks at the triangle and it's the triangle is back-facing, so I'm not going to draw it. So you just wasted a whole bunch of vertex processing and rasterizer throughput to figure out that you don't have to render half of the mesh. Great. Mesh shaders give you a way, for example, to do this culling on a higher level. So instead of everybody does frustum culling for meshes, right? But meshes are large, and a mesh of a character is has both front-facing triangles and back-facing triangles. But a meshlet might not have front-facing triangles, and there's ways to do ahead of time. So you can ahead of time build basically a cone within which a camera will never see a meshlet. And this cone might be fairly wide. And so if the camera is inside the cone, we have a static guarantee that the entire meshlet, all triangles in the meshlet, are back-facing from any point within that cone. Meshoptimizer has a function that helps you do this. And this, it doesn't do perfect, like it's a conservative approximation. It can't ever, like if a triangle potentially is visible, it has to tell that some of the triangles might be. But you can build this conservative approximation, and if you use it, you can reject the entire meshlet for some number of meshlet basically can be rejected by not even looking at the individual triangles. Similarly, if you have an occlusion calling setup in your engine, which modern engines should do, there's a way to do this that's like basically perfect. But if you have occlusion calling, you can even set things up such that the characters, meshlets in the back of the character, even if some of them have complex geometry, so it's like partially front-facing, partially back-facing, your occlusion calling system could call it away because it's occluded by sort of the front of the character. And I will not go into details, but basically you can do this. And once you do this with meshlets, you have much higher rates of calling, because if you do something on a mesh level, if you see a character, right, if you see even a small portion of the character, it would be a waste to process the whole character. And so meshlet-based pipelines give you a way to do a lot of these optimization phases in your runtime shaders on a sort of medium granularity. It's smaller granularity than the whole mesh, but it's larger than a single triangle. And so for this, they're like very, very good. You can build very efficient pipelines with them. And then we talked about quantization. Well, if the vertices of the meshlet are in a tight sort of proximity, the bounding box for the meshlet can be very small, which means you might need much fewer bits to represent each coordinate within the meshlet, because you could have, per meshlet, you could store like a bounding box, and then every vertex inside the meshlet could be relative to this. All of this has complex stuff that I'm not going to talk about, and also Meshoptimizer doesn't help you with some of this, because it's like, oh, yeah, I can quantize vertices within the meshlet, but then a meshlet next to it shares some of the vertices. And if you quantize a vertex on the boundary between two meshlets in different ways, you will see gaps. So how do you not do this? How do you quantize sort of without this? There's ways to do this. So you mentioned Meshoptimizer documentation. Meshoptimizer documentation doesn't talk about things that Meshoptimizer is literally not involved in. Sometimes that's not great. I have a couple plans for additional sections at some point that talk about like, so you like integrated Meshoptimizer, now what, right? Basically, what are the problems that are adjacent to the things that Meshoptimizer solves directly that it can kind of put you on the right path, right, without like even having necessarily functionality for it. But anyway, so yeah, so this is meshlets. Meshlets are interesting because it's kind of an evolving space. Everything that we've talked about with Vertex cache and stuff like this, it's kind of, old story. It's been there for years. People have done this, etc. The mesh shading related functionality is new, fresh, and evolving. So for example, last year, I've added a new optimization algorithm for meshlet partitioning that takes a mesh and gives you a set of meshlets. I have 2 of them now. The reason why I have 2 of them now is that NVIDIA now has support for ray tracing from meshlet data. It's NVIDIA only right now. I don't know if it whatever the AMD story for this is, I don't know. But if you're on NVIDIA hardware, you can do meshlet-based ray tracing. They call it, there's a marketing term called RTX megageometry. But the thing about that is the criteria for how you split a mesh into meshlets differ a lot based on whether you use rasterization or ray tracing. Because when you use rasterization, you're concerned about the efficiency of the rasterization stages and how well things are like packed and stuff. And when you do ray tracing, you're really concerned about the boundaries between the meshlets and how like axis aligned they are, because the ray tracing hardware builds like axis aligned BVH structures around this. So it's different problems. There is not a single, if you built a single set of meshlet data, it would be suboptimal for one of them. And interestingly, the suboptimality for ray tracing is much worse in the sense that, so if you took raster data and gave it to the ray tracing stuff, you would see more of a performance drop versus if you took the ray tracing optimal structures and you used a raster pipeline. So you could have a game where you almost don't use ray tracing, in which case, even if you use these extensions, the raster only data is fine. You could have a game where you mostly run ray tracing with occasional rasterization, in which case ray tracing data is fine. If you have a game that wants both to be optimal, I don't know what you do. I don't work in games, I just work on libraries. This is like not ideal, but this is kind of how the world works, right? I think the mesh optimizer tries to kind of embrace and grapple with the real problems of how the real world, how the real hardware, how the sort of real engine pipelines work. Without, like, you can't wave away something like this where it's like, oh, like the data is just has fundamentally different efficiency properties. So anyway, and this new algorithm is literally new as of last year, because NVIDIA only released this like new capability last year, so it only really became important last year, right? So a lot of the stuff is like evolving, but yeah.
Okay. For people who are following, to make sure that like they're still on board, we first talked about...
I'm assuming we lost everybody, no, that's...
People are still there. Vertex shader, rasterization, and fragment shader. This is the traditional pipeline that's heavily used. And this is what we discussed in the beginning with vertex buffers and index buffers, of the ordering and stuff. Now we talked about replacing vertex shader with mesh, a new concept regarding meshlets. This was the second part of and with both, mesh optimizer helps and has functions that you can call. Now we're moving forward. I feel like we're skipping mesh compression, or do you think we should talk about it?
Let me briefly, I'm going to cover it in 5 minutes. I think mesh compression is interesting to talk about, just also because it's like a different way how to use the library. That's not like the other ways. So when we talked about the other ways, we said, okay, it's usually an offline process. Sometimes you use procedural geometry, but like often you don't, right? You do this offline. So the other thing that Mesh Optimizer has is it has several compression algorithms that are specialized towards mesh data. So you give it vertex buffers or you give it index buffers. I'm working on a new thing where you give it meshlet data. It's not fully ready yet, but it's coming along. And so it compresses it and then it decompresses it at runtime, like very straightforward. You can think about this as, I don't want to use the word replacement, but you can think of it like a traditional general purpose compression algorithm like a Z-standard or zlib or whatever. So there is a question of why, the reason why these are different at all is that if you compress the data, you need to decompress it, right? So the idea is in your offline tool chain, you use mesh optimizer algorithms to compress your data after you've like prepared it optimally and stuff like this. And then in your asset streaming code at runtime, you load the bytes from disk, from whatever, that don't have the GPU-ready representation yet because they're compressed, and then use mesh optimizer algorithm to decompress it. So this is the one case where you kind of have to link the library into the engine runtime code, right? Because you have to decompress it. So I don't want to talk about the details, are very interesting and complicated. I don't want to talk about them, or we just don't really have time to talk about them. But so like, why do they exist is the question, because there is zlib and Z-standard and stuff like this, right? There's two things to say about this. So one is there is a lot of types of redundancy in the mesh data that traditional algorithms can't recognize because they don't know what to look for. The basic thing is the vertices are likely to be close to each other, And so even if you just do delta compression on the vertices, then you will have a better result. But the general purpose algorithms like zstandard or zlib or whatever, they don't do delta compression because they don't know what your data is structured. They just look at it as a set of bytes and try to find matches in bytes or try to build statistics around bytes. The triangle data, the index data has the crazy amount of sort of redundancy inherent in it, especially for optimized index buffers, that none of these algorithms recognize very well. And so you will compress your mesh data with traditional algorithms. They will work. They will not give you as good of a compression rate. But also, some of these types of compression can be restrictive in ways that make it much faster to decompress. So the Vertex compressor is an interesting example. It's kind of counterintuitive, but here's the deal. So you can compress with zstandard, and it's going to be fine. And zstandard will decompress at around 1.5 gigabytes per second on my system, on my desktop system. Zstandard decompresses around 1.5 gigabytes per second of mesh data per core. So if you have more cores, you have more, you can decompress more. If you have a worse CPU, so on something like a Steam Deck, it's much less. My algorithms usually can compress the Vertex data a little bit better than zstandard out of the box. They will decompress 3 times faster. But the reason why they decompress 3 times faster is I can't replace zstandard. I don't know, maybe I could. The big reason why I don't even want to go and replace zstandard completely is so on consoles, you have, I forget, on some PlayStation models, they have hardware accelerated decompressor that is better than I think even zstandard in terms of compression ratio, but it's in hardware. And so you can't compete with that. It's an impossible job. And so instead of competing with zstandard in the sense of replicating what it does, plus adding more things that it doesn't do, I do things that it doesn't do and don't do things that it does do. What it means is that my compressed representation can be then compressed again, which is usually you don't usually think it's a bad property, right? Usually if you have a zip file, you can't zip it again and reduce the size. That makes no sense. But with my data, you can take this data and then again zstandard it or zlib or whatever. And usually you get it to be smaller further, right? So when you use meshoptimizer compression, you kind of have options. You can say, oh, I'm just going to compress with meshoptimizer and it's small enough. I'm just going to ship it and it will decompress much faster. Or you could say, well, it's not small enough, so I will take the output. I will compress it again with zstandard. And then when I decompress, I have to decompress twice. Zstandard decompresses and then meshoptimizer decompresses. But because the zstandard decompression decompresses less data, because it decompresses into a compressed representation, if that makes sense, it runs faster. It's still 1.5 or whatever gigabytes per second, but it needs to output 3 times less data, and so it runs 3 times less time. And so the total output is still faster to decompress than just using zstandard, and it's much smaller. So this is an interesting space because it's super difficult to navigate, because you have all of these conflicting requirements. It's oh, should the data be small enough? Should the data be fast to decompress? How small is small enough? Compression has these horrible curves where people who do compression for zstandard type stuff, right? They would usually kill for a 1% extra compression ratio. And you could have a compressor that gets you 5% more compression ratio, but takes 10 times longer to decompress.
Yeah.
And in some spaces in compression, this is a welcome thing. And it's kind of a fundamental property of the space. At some point, you have to spend way too much extra time to get enough of extra compression savings. Because of this, I have this layering property, right? And also, I just don't want to compete with all of this. But the final thing I'll say is, one of the motivation for why all of this is valuable is just the disks are getting faster. So 10 years ago, it didn't matter as much. It's probably more than 10 years, but like 20 years ago. So when you have a hard drive and it reads like 100 megabytes per second in a good day, then it's like if your compression algorithm can decompress at a gigabyte per second, then you're already way faster than your hard drive. If your SSD can read 4 gigabytes a second, and modern SSDs can read in that ballpark or higher, if your decompression algorithm decompresses at 2 gigabytes a second, you could be better off just storing uncompressed data on disk. Like, yes, it will be larger on disk, but it will take less time to read, unless you can use multiple cores to decompress. But if you use multiple cores and you're streaming data, which usually are in modern games, then you're taking away CPU resources from the rest of the game. So there's like lots of trade-offs here, but because of this, basically I saw this space of, I want to have compression algorithms that work really well for mesh data, that are not peak size, like it's not the minimum amount of bytes that you can squeeze a mesh into. But given that I want to decode at like many gigabytes per second, right, on modern hardware, how small can I get it? And if you want more space savings, then you can use the standard and stuff to compress it. So,
okay.
So this is the one case where you basically have to use Mesh Optimizer at runtime, but you don't have to use. So again, Mesh Optimizer is like a collection of tools, right? If you don't like compression algorithms, like don't use them. If you like one of them but don't like the other one, like don't use it. It's fine. Some of the production games use them. Some of the production games that use Mesh Optimizer don't use them, and it's I'm not. I'm judging a little bit, but I'm not judging too harshly. As long as you use some work.
Judging just a little bit, just a tiny bit.
Yeah.
Next on the list is mesh simplification.
All right. Great.
We're going deep on this one. I think so.
Are we? Oh my god. Okay, so I don't. This is the fun thing. Maybe it will give people a little bit of a perspective. So this is probably one of my least favorite areas of the library, but also
really?
So I have a love-hate relationship with this area of the library. Let me put it like this.
Okay.
So what does it do? I give you a mesh. So far we've discussed algorithms that either don't change the appearance of the mesh or that change it in quantization case, but they change it in like a predictable way. Like, I give you a vertex, you like throw away half of the bits of the position. Okay, the vertex is going to shift. Simplification, people call it decimation, people call it mesh reduction. It basically says, here's the new mesh that kind of looks approximately like the mesh that you gave me, doesn't look as nice, but has half as many triangles, right? And then you use it in two cases, really. Usually you use it to just build level of detail data. So you take a mesh, you build a simplified version of the mesh that you swap in at some distance. You can simplify the original mesh. I think it's usually called like level of detail 0 simplification or something in some engines. But basically, if I gave you like a scan, like a 3D scan, or if I gave you a mesh that just has an insane resolution and you just imported it in an engine, you may never want to render it. It may just have too many triangles. So like, maybe just not be a good idea to do it. But that's the basic idea. It's very, very simple. You give me a mesh, I give you a mesh with fewer triangles. So this is a terrible problem because people like the way the meshes look. And it's so easy for a human eye to spot imperfections that are way less obvious for an algorithm. So much so, it's difficult to get. There are some metrics that measure like the deviation between the level of detail and the source, but even that is hard. That is hard, and so in 2D images, there is like decades of research of metrics, of similarity metrics, right? Like, does a human think this image looks perceptually indistinguishable from another image? Even that is a hard problem. Meshes are like, harder problem because you could render a mesh from a given angle and you could compare the image, but what if the angle changes? What if the scale changes? What if differences in different attributes influence the appearance based on the shading that you use? Like, the silhouette of the image looks fine, but the shading is all broken up because some normals don't look properly on the resulting mesh. So this is a difficult problem. I built an algorithm for this, like a first basic algorithm, like many years ago. And then, so here's what happens with algorithms like this. You run an algorithm on a mesh. So the first problem actually is actually more fundamental, I guess. So most of the research for this comes from the 90s. There is like a couple of papers. I think 1999 is the last super important paper. And in the last 26 years, you could ignore, there are some papers. Some of them are like valuable, but you could ignore them and it could be fine. Which is an unfortunate property because clearly in the last 25 years, things have changed in the rendering space in general, right? But the fundamental research hasn't really changed. The fundamental research that powers a lot of the algorithms. And the fundamental research is very, it's great and not great at the same time. It forms a good, so there's a thing called quadrics, which is basically a way to approximate how a portion of the mesh surface looks like using like a small number of floats. And then you can use this to both measure the error, I built this functional approximation for like this mesh, and then I simplify it a bunch, and then I compute this function again for a simplified subset. It gives you the error, and it also gives you information to reduce complexity in the mesh by basically just looking at areas of the mesh where this function tells you the error is low, and like simplifying them by removing triangles. There's like the foundational element of most of these algorithms is called edge collapse, where you just take an edge and then just fuse the two vertices together, which removes two triangles that were connected like to the mesh like this, right? So it removes two triangles, and if you remove two triangles at a time, eventually you'll get a mesh that's much smaller. The problem is, so it's very, very easy for a human to look at the result and say the result is obviously broken because, this thing shouldn't be there and this thing shouldn't be there. And there is relatively few algorithms, and again, like not a lot new since like 1999, that have meaningfully different sort of, people write papers that are like, oh, we tried this thing and it made the thing like better, and we shipped it. And this is true, but there's few like kind of foundationally new things in that space. And it's fundamentally difficult because you have this sort of thing, you have an appearance of the mesh that is judged by a human. And to get to this appearance, you run a bunch of shaders that you don't know what they do. There's all sorts of like strange stuff that happens. So let's say you have a mesh and the mesh has textures, which they usually do. And textures have gaps. So if any artists ever try to like UV map a mesh, it's like so actually this is interesting. A thing that artists hate the most, as far as I can tell, is UV unwrapping. And the thing that's also really terrible for simplification is the presence of unwrapped UVs. So there is a lot of commonalities here. But so you have a UV unwrap. Let's say you have character's hand. And the character hand has fingers. And when these fingers are unwrapped on a flat texture, you have to like cut the sort of the mapping around some edges that are usually called UV seams. And usually what happens is inside the texture, you have like, for example, you have like the front side of the finger in like one place of the texture and the back side of a finger in another place of the texture. And when the artist paints the texture, when some algorithms paints the textures, they like ensure the edges line up very neatly. And, a human looks at this and you can't see the difference. And then the simplification algorithm comes along and it's like, well, I don't like this edge. Let me like contract this edge. And something terrible happens in the texture. And so there's many different ways, and so the reason why it's difficult to work on these algorithms is you run the algorithm on the mesh, the output looks bad. You're like depressed because what are you going to do? So the algorithm makes certain decisions. Some of them are wrong. So you can improve the algorithm. Sometimes the algorithm makes decisions that are correct, as in the algorithm's mathematical model is perfectly implemented in the code. It just doesn't work very well, and it's like not clear what to do about this, right? So it's fundamentally a thing that has so much subjective, like human intuition built into the judgment of the result. But also, all of the other things that I've already talked about layer on top of this. So I don't want a simplification algorithm that takes minutes to simplify a mesh. They exist. Sometimes they're better than what meshoptimizer does in, I'd say, so what meshoptimizer does in like everything else is basically better than, I haven't seen things that do it worse. Simplification is the area where I can't claim, oh, it's better than everything else you'll find there, like it's not. Part of the reason is it does things differently in ways that are like important structurally, but so basically there's extra restrictions that I haven't talked about that I probably won't talk about that make it more difficult to do a good job. But also I just don't want the thing to be very slow. And so because I don't want the thing to be very slow, I'm limited in the things that the algorithm can consider, which makes the output be not as good. Or another example is, so I talked about the textures. If you have a texture mapped, at some point, ideally, if you are generating LODs, you have to switch to a different layout of a texture. So there are some commercial simplification tools that do this process called remeshing and then retexturing, I guess, where they take like a house. So a house is a great, terrible example. So you take a house. The only way to build a good level of detail of a house that's like much smaller is to build basically a new mesh that looks the same but doesn't use the original texture, because you have to take the source texture, you have to like take some of the pixels out of it that did matter. But if you take a house and you like replacing it with a box, the box should have like details of the windows and stuff like this. Some of them were modeled with geometry in the original mesh. Some of them were modeled in textures, but the parts of the textures where they are all over the place because the unwrapping kind of followed the geometric shape. And so you kind of have to rebuild like the whole thing. But so it's called mesh optimizer, it's not called texture optimizer. So it doesn't, it's some cases it's painful to integrate something that needs new textures for new LODs, and it's sometimes less efficient. And so Mesh Optimizer basically tries to solve a subset of this problem. I was very unhappy with the current state of this for like many years while I was not working on this, because so I worked on this code at some point, and then I looked at the results and I'm like, man, I kind of don't like the results, and then it's difficult to motivate yourself to improve it. So I've worked on this a bunch more in the last 2 years, and I think I'm now content with the algorithm, as in there's choices that it makes that are terrible, but it's like you like your kids even if they do terrible things. So I guess I'm at that stage.
High level, what have you changed? Like very high.
So there's a lot of stuff that goes really in the details of. So one interesting thing is so when you do these simplification decisions, you have to evaluate the error. And the original version that I built a long time ago didn't really look closely at the attribute data. So it would just evaluate the error of positions, and it would ignore the attributes. So that's bad if you ever have like normals or whatever. And this is where there's a problem. So if you look at the research of the sort of from the 1999 of how to solve the problem, they tell you, well, you can build a functional approximation of the error that doesn't just look at positions, that also looks at attributes. And there's a way to like efficiently compute this and stuff like this, but let's say you have an edge collapse that changes the position and changes the attributes. I mean, they always do. But you have to figure out, is this edge collapse better than some other edge that maybe changes positions less, but attributes more? And also there's a question as to what does an attribute change even mean, in the sense that, so if I change the attribute a little bit, but the change is over the entire triangle. So let's say I have a large triangle and I take one vertex of it and I just tweak the normal a little bit there. You could have a large perceptual change because the triangle area is so large that the shading changed a little bit. But because the area is so large, the human eye is like, oh wow, like this was a LOD change, right? Whereas if the triangle was very small, but the change was more abrupt in the attribute, sometimes it's more acceptable. But the other really difficult part in all of this is that the mechanism that I described, the edge collapses one edge. You need to collapse like lots of edges. And how the error accumulates during these collapses is very difficult to model precisely unless you have like too much time, unless you can take minutes to simplify mesh. It's difficult to model like the accumulated error well. And so the research from 1999 kind of doesn't tell you to do the right thing. And I haven't really seen anything published since that tells you how to do things differently. Plus, I had a bunch of like some bugs and some other stuff in the way the error is accumulated. And so basically the state of this was, years ago, I wrote some code that takes attribute values into consideration, and it worked. And it looked similar to what I can see the research from like 25 years ago doing, but it didn't look very good. And so I was like, I don't know what I do. So yeah, so since then I figured out some things around the math there that were like not right. I figured out some bugs. There are some things that, because my algorithm is prioritizing the performance of generating the output result, to an extent, it's not the ultimate priority, but it is a priority. There is, again, certain things that I have to do differently, and that stuff is just not like you read any source code that's not meshoptimizer and it doesn't do things this way. And because of this, it's also difficult to, it's like, is there a bug here? Is there not a bug? So I fixed a lot of bugs. I came up with like a different way to combine these errors between attributes and positions. And then I came up with some other modes that I can't really explain. It's too much in the weeds. But some of the internal basically of how the algorithm decides if it's safe to collapse an edge have changed to make some things like more permissible. And so the aggregate of all of these changes, right, means that it's like pretty decent now. There are still many problems, or not that many. I think like every time I look at this again, I'm like, okay, there's fewer problems. And so like, it's getting pretty good. There are still cases where basically there are still sort of bugs that are not fully clear how to fix, right? Even debugging this stuff takes forever because you have a mesh and something happened during the whole sequence that made the mesh look not very good. But you have to look at how we got there. There's usually one specific step in the algorithm that causes the most apparent visual change. But going back to what we discussed earlier, it may be a well-intentioned step. Like the algorithm looks at the state that it's at, and it's like, oh, this looks good, and it's not good. But to figure out why it's not good, you have to consider all of the past decisions that the algorithm has made, and it's like difficult to do. So yeah, I think it's just an inherently like frustrating problem in some sense, just because there's no optimum. It's difficult to measure the optimum. There's so much subjectivity, and there's so much variability in how you might use it, how you might not use it. Like, do you have different attributes? How does your shader work? What do you compare to? Because sometimes, for example, it's easier if you have a mesh that doesn't have UV unwrapping, then you can get a much cleaner shape of the output. But the shape has to be re-unwrapped, which is not good. And so preserving the UV mapping while the simplification process is going on puts enough of the extra restrictions that it's like, oh, meshes with clean UV mapping, for example, with Mesh Optimizer, they simplify way better than meshes with really bad UV mapping. And so depending on like the UV mapping that you have and stuff like this, you will have different results. So the algorithm is production ready, to be clear. Like there's games that use it, there's production games that use it. It's I think the fundamental problem has so much inherent like oddities that it's always difficult to say, oh, this is good enough, because it's kind of never good enough. So
okay,
that's
okay. This was simplification or mesh decimation, so
right.
Trying to disappear a couple of triangles so that the mesh is simpler, especially used for a lot of detailed stuff. Now we enter Nanite style geometry, virtualized geometry, in mesh optimizer known as glTF. Can you tell me about that?
So So everything that I told you about the simplification just now, and actually everything that I told you about all of the other areas of the mesh, they would usually work in, they would consider the mesh as a unit of operation, right? Sometimes maybe you have a mesh subset. Sometimes if you do simplification, you may want to simplify like a bunch of meshes even at once. But the usual approach is you take a mesh and then you do a bunch of operations to it, and then you get a different mesh. Sometimes it's simpler. Sometimes it has like fewer triangles, right? Sometimes it has fewer vertices. Sometimes it has different orders so that it's more efficient to render. And then you can feed the result to the GPU, and the GPU will be happy. So with simplification specifically, one challenge is usually the way you would integrate this is you would build levels of detail. And it's what's usually called discrete levels of detail. So there is a level of detail 0, and then there's a level of detail 1, and then there's a level of detail 2. And there is thresholding in engines for when to switch between one and the other. The configuration of the thresholding is a separate can of worms. Like there is like distance based and like screen area based, and all of this is pretty bad because it doesn't consider the deformation in the mesh. Mesh Optimizer has like an error metric for this, which works pretty well. But even then, there's at some point a decision that the engine makes at runtime to switch from mesh to mesh, from mesh LOD to mesh LOD. And this usually is causing pops. These days, most engines do temporal anti-aliasing of various ways, which has a hilarious side effect of kind of sometimes doing a crossfade between the level of detail like automatically, because like it looks at the previous object that you've rendered, it's roughly at the same depth, it's roughly at the same color, it's like, it's good enough, I'm gonna like blend between them, and they can get hidden a little bit, but fundamentally you're changing the mesh that you're rendering, right? So it's not visually pleasing. And then the other problem, so I've told you the mesh optimizer side of simplification, right? So you have an algorithm, it can like build a simpler version, stuff like this. In the industry, so you could use that. Some people do. You could use other commercial offerings. There's like Simpligon and some other stuff. They are usually artist-driven. There's usually semi-auto. So Mesh Optimizer thing is completely automatic, and the commercial ones are usually partially artist-driven, as in like an artist presses a button and it gives it an ULOD, and then they're like, yeah, I don't like this one. Sometimes there is ways to, for example, if you have a character, you could paint the weighting of the priority of the different areas of the character. Mesh Optimizer has library support for this, but it's not a tool, like it's not a plugin, right? And so some plugins that are proprietary, they give you ways to like control this, right? And so at some point the artist is like, this looks good enough, ship it. So there's a human in the loop. Sometimes the artists do the LODs by hand. This still happens today. Especially, so Mesh Optimizer works reasonably well on a certain simplification range and certain geometric style. There's some geometric styles where it's very difficult to build. So there's some geometric styles where Mesh Optimizer doesn't do the right thing, but also there's some geometric styles where it's just like super hard even with all of the techniques I mentioned that Mesh Optimizer doesn't do, like the remeshing with retexturing, you still get terrible results. Sometimes the only clean way to do this is to get a human and like have them do the thing. And so some games have artist budgets for honestly what's grueling and like, I don't know, not creative work at all, which is like, here's a mesh that has 1,000 triangles. It has to be 100 triangles. I don't care what you do, but it should look exactly like this from a given distance. And it's like, okay, great. What am I doing here? So on the flip side of this, there is workflows where you do 3D scans and you get a mesh with like millions of triangles. So Quixel works like this. Like you can go to Quixel, I think it's called Quixel site. They have like rock models there that are 3D scanned and meshed. And so you download a 3D model, and then it's like, 4 million triangles for a single rock. And also I should not bring up GenAI. Hopefully you're not using GenAI for meshing, but if you are, that geometry is also terrible. So this is a difficult space to work with, right? Because you have a human in the loop sometimes, and if you don't have a human in the loop, sometimes the results are not very good. Whenever a switch happens between LEDs, the switch is instantaneous for the whole mesh. I should say there is research from the 90s around continuous level of detail. But that research doesn't work today at all because it has a very different hardware model in mind. A simplified explanation would be, there is research from the 90s called progressive meshes. You can use it today. It's bad for 2 reasons. One is the CPU has to do too much work. There's some research that avoids this, but to kind of simplify the mesh on the fly to smaller numbers of triangles. 2 is the resulting mesh, even in methods that are optimized for the CPU, it's not vertex cache efficient. It turns out that if you have a mesh that's not vertex cache efficient, you could render a mesh with way more triangles for the same cost that would look nicer. And so these are kind of in tension, right? The goal is not to simplify at any cost. The goal is not to reduce the triangle count at any cost. The goal is minimal perceptual loss, but also hardware efficiency. And so it's hard to reconcile all of these. So Epic released research in 2021, I think, or so, which is kind of industry defining because it gave the industry a new path that engines since then have started implementing. So you had folks from Ubisoft. I'm blanking on the name, sorry.
Nicola Lopez.
Yeah. So I think they talked about sort of micropolygon rendering in their latest Assassin's Creed games. There's some other games that are starting to do this. But so there is this trend, which is basically Nanite, but Nanite is an Epic technology that is now just part of Unreal Engine. So what Nanite does is fundamentally a way to do continuous LOD, but it is based on a cluster hierarchy. So think about this way. You split the mesh into clusters, and then you take a bunch of clusters that are near each other. You take them out of the mesh, then you simplify the result. You simplify the resulting groups of clusters. You get fewer triangles. And then you split the thing back into clusters. And then you put the resulting clusters back into the mesh, and then you repeat the process. But every time you do this, you remember all of the intermediate decisions and data that you have made. So your final output is not a simplified mesh. Your final output is every simplified cluster set that you have made during this process. And the reason why that's important is, and there's caveats around how do you deal with boundaries with clusters, and there's caveats around hardware efficiency and all of this, because once you build this hierarchy, there's 2 hard problems here. First is you build the hierarchy, and then the second one is the runtime component that actually takes this hierarchy and then has a mesh that is in a given place in the view frustum and asks which clusters in this giant hierarchy should I pick such that the visual error that would represent the switch from the original mesh to the set of clusters is minimized. But this is not discrete it's similar to the thing I was talking about earlier around meshlet calling, where you make decisions on the meshlet level. Here you make decisions not quite at the meshlet level, but the simplified way to think about this is you take clusters that are too detailed for how far back they are in the refrostum, and then you replace them with simplified clusters that you have prepared earlier. And you can do this at different depths, at different places in your mesh. Like maybe part of your mesh is closer to the frostum and part of the mesh is farther. So the part that's closer, you keep more high resolution clusters. Maybe some parts are so far away that you replace like hundreds of clusters with just one. It's complicated because you have to make sure you don't introduce gaps. If you just take a few clusters and then simplify them, you have to preserve the boundary. And how to preserve the boundary, but how to have an algorithm that builds this whole giant hierarchy is like a difficult problem. And then once you have done this, how to map it to hardware is a difficult problem because I've talked about mesh shaders, but mesh shaders take one meshlet and then make decisions in that context. Here you have what's potentially millions of meshlets in your original data, which is like hundreds of millions of triangles. How do you efficiently do this LOD selection per meshlet, basically, per meshlet group? And how do you produce this set of clusters is complicated. Plus, Nanite has extra runtime craziness because their triangles are so small, they target triangles that are under a pixel large. Because the notion then is this. So I told you how switching from LOD to LOD is perceptually obvious because you've just changed the whole mesh. So the Nanite idea is like this. What if every triangle was targeting around the size of the pixel on screen? Then if you have a cluster that has triangles that are too dense on screen, you swap it out with it at some point, like they become a little bit too small. So a mesh increases the distance from the camera. The triangles get smaller on screen. At some point, they go from being 1.1 pixel on average to being like 0.7 pixels on average. And you're like, okay, cool, I'm gonna like swap out a bunch of clusters with different clusters. But every error in every swap like this is pixel level because you took a bunch of triangles that were very tiny and you just replaced them. And the idea is you will see a transition, but the temporal anti-aliasing will perfectly smooth out the transition because transition is under a pixel large. And literally the whole job of temporal anti-aliasing algorithms is to remove the shimmering and the aliasing that happens when it's under a pixel. So this is the idea, right? Because of this, they end up, by design, they want to render tiny triangles. And so they had to write like a software rasterizer to complement the hardware rasterizer to render triangles more efficiently and stuff like this. But the mesh optimizer part of this is less scary because it's asking this question, can you build a hierarchy of clusters? So it turns out Mesh Optimizer can build clusters for a mesh because mesh shading. Turns out Mesh Optimizer can simplify meshes. When you simplify meshes, you take the whole mesh and you simplify it, but you can tweak the algorithm in various ways to be able to take a subset and say, okay, I will preserve the boundary edges of the subset. I will like simplify the internals. The other important property of this pipeline is there's no human in the loop. There can't be a human in the loop because every transition is on a cluster level at different points in different parts of the mesh. You can have a human like bias heuristics. You can be like, oh, like this mesh should have twice as much detail on screen as the other meshes do, and it will like bias all of the transitions. But you can't be like, this cluster looks bad, let me remodel it, right? Like there's too many of them. When you decide when to switch from cluster A to cluster B, you need to have metrics that approximate visually. So like you have a number that says, I think the error on screen will be around the pixel between these two, apparent error, right? Turns out Mesh Optimizer kind of has to do this, right? So Mesh Optimizer landed in a funny spot where, unrelated to all of the Nanite stuff, enough of the components of this theoretical system kind of were, 80% there. And so I kind of figured why not go 100%. But the thing about going 100%, so there's a component of Mesh Optimizer project which is not a mesh optimizer library, which is called cluster.load.h, which is a header file. It's kind of an STB style header file, so it's like a single header. It's designed to just be copied in your project, like you include it in the source file and stuff. And what it does is it calls a bunch of different mesh optimizer functions, but it has fairly little complicated logic by itself, because it's modeling the higher order algorithm of how to build this hierarchy of clusters and how to simplify them and stuff like this. So the thing about this is it's combining a bunch of mesh optimizer algorithms, but it does it in a somewhat specific way, and maybe you have a different way. Maybe you don't like half of this and you don't like the other half, right? Or maybe, so it uses specific simplifier from mesh optimizer, and it uses some specific clustering and partitioning algorithms that we haven't talked about and stuff like this. Maybe you want to use a different partitioning algorithm, but you still want to use this simplification code and this higher level loop. So this basically lives somewhere on the boundary between example code, but it's like 600 lines of code or whatever. So it's not example because it's too complicated to be an example. And you can take it and use it as is, but also some parts may not work well for your specific engine situation. Maybe some parts are underdeveloped. I don't know, this thing hasn't seen production usage yet. And so because of this, it's kind of a separate thing, right? That if you want to use it as a single header thing for just copying into your project and doing whatever with it, it's fine. If you don't like half of it, you can rewrite half of it. You can also just read it as these documentation, but in the code, in the sense that if you want to build your own thing that uses mesh optimizer, for example, but does different decisions, you still probably should read this flow to understand exactly how it works, so that you can then implement something like this, right? So it's kind of somewhere between example code and production library. You can take it as is, you can take it as is and change half of it, you can take it and then just read it and then, not use it, it's fine. So this is a separate part of the mesh optimizer, and because the runtime version of this is draw me the rest of the owl type of thing, where you have to do a bunch of shaders that do complicated stuff. It's less, even once you add the header to your engine and once you call the right functions, you get a bunch of data. What do you do with the data? There is a great NVIDIA project called VK Load Clusters. It's a Vulkan example that basically does the other half. So it uses mesh optimizer cluster load.h to generate the data. And then they have this whole pipeline of, because one thing I haven't talked about, for example, is streaming. If you start with meshes that are tens of millions of triangles, and you hundreds of millions of triangles, I don't know, and you can display them as just a few triangles on screen, if the mesh is far away, you kind of don't want to have the whole 100 million triangle monster in your memory, right? And so I think inherent in the notion of Nanite is the fact that at runtime, you stream parts of the mesh. So parts of this, you can imagine this is like a giant tree of clusters, where the further you go into the tree, the more you replace simpler geometry with complex geometry. And at the very bottom of the tree, you have the original mesh subdivided into clusters. And so you have to do streaming, where you take this tree and sort of page in portions of that tree that you can then compose into a mesh on screen. And then there's all of the shaders that actually have to figure out what to draw and stream. And so runtime for this is complicated. I'm kind of, so Nanite, on one hand, Nanite is super interesting as a new technology, and Nanite style technologies, right? It's a new way to think about geometry rendering, which is very interesting. On the other hand, man, is it difficult to implement and integrate. Even mesh optimizer, it helps you, it does this cluster load stuff for you, but the runtime itself is very complicated and compression is complicated. And with the rest of the mesh optimizer, it's so nice that you could have a very simple renderer that just renders meshes, And then you can go from like no mesh to mesh on screen in like a couple hours of like just writing raw graphics code, maybe less if you're an expert. And with Nanite, it's like a lot of work to build the runtime. This is like an example of basically a new thing in computer graphics. So mesh shaders replace earlier shader stages, but if you're not doing anything fancy, they're not actually harder to get started with than Vertex shaders. You need to build like data a little bit differently. Meshoptimizer does this for you. The runtime is very simple. Nanite is like the example where the runtime is very difficult to implement and to tune performance-wise and stuff like this. And even that is not the end, because if you look at the Unreal's like latest developments, they have this thing called Nanite for foliage now, where they can take this tree and replace parts of it with voxels. Meshoptimizer doesn't have this yet, or doesn't have this period. I'm not sure if I'll ever get there. But basically, this whole they built really new, really cool technology that's also so complicated that I don't love the fact that it's so complicated, if that makes sense. I don't have like a great alternative other than to not do it and do things that way, but I should say, there are benefits and drawbacks to this technique, right? It is nice to be able to tell your artist just dump like hundreds of millions of triangles into the asset pipeline and be done with it. But I don't know that it's globally optimal. Like basically, this is almost the reason why this thing exists. It's like saying, what if artists never had to care about the complexity of the data that goes in? And on one hand, it's good because it sort of gives artists complete artistic freedom over what they want to do. But on the other hand, the whole thing becomes so complex that I feel like maybe there is some better way to do this, so that, yeah. Anyway, so it's very, very cool. It's very interesting. But I have not also, for example, so I have a renderer that I occasionally develop on streams that does like level of detail and occlusion culling and like mesh shading and all of this. It uses Meshoptimizer. It does not have Nanite-like rendering, and I do not plan on doing this just because it's so much work, and I do most of that work on streams, and it would be like weeks of streaming, I feel like, to figure out all of the runtime bugs and to deal with the GPU crashes and to optimize stuff to just get to the thing that works. So I'm super happy that NVIDIA has a sample. So, VK lot clusters, it's very clean Vulkan code. It's Vulkan specific, but, it's very, very clean. It's easy to read. And it uses Meshoptimizer. So there's nothing not to like.
VK lot clusters. That's the
VK
name.
_lot _clusters. Yeah. It's a GitHub project. You can just check it out. I know roughly everything that goes into it.
That's already...
And even then, yeah. I feel like it's at least a couple weeks to get components together, as in... But if you include optimizations and stuff, I don't know, it's like a month easily. I don't know, multiple weeks of work for sure, but I think if you include performance, it can easily be months. So people used to say this about temporal anti-aliasing, that it's like... you need a full-time engineer, not because it takes you like years of work to do this, but because you implement it and then something breaks, you discover an edge case and then you figure out how to fix this and then you discover an optimization and etc. So I think it's complicated sort of from this perspective, and not because the underlying like techniques are well known and well studied, and so you can do them. But yeah, like fully finishing this would take a long time in the production scenario, just because you keep discovering things that break, and you keep discovering, you do streaming, but then you want to compress the data, and then so you do some custom compression, and then you even there's difficult aspects. Here's the easiest way maybe to talk about this. So I told you that there's this tree. And so your job is to find, it's called the cut of this tree, and the cut, because you can literally visually represent it as like a line that goes through the tree, that goes between different levels of the tree, right? So it's like, okay, we need this subtree and then this higher level of this subtree next to it and stuff. Okay. If I were to build the first version of the thing that takes the cut of the tree, it would take me like an hour or two. Why? There's a very, very easy way to do this. The way to do this goes like this. For every cluster, you basically have a float that tells you the error of the cluster, and you can take this float to convert it to a binary decision, which is this cluster good enough or not? Cluster.h has like, it has this float, it has like comments that nicely tell you how to use this float to do stuff, etc. You can literally write a compute shader that goes over every cluster in your entire cluster tree, takes this float, asks, is the cluster good enough or not? And then like renders it or not. The properties of the tree construction are such that if a cluster tells you it's not good enough, there's going to be a cluster above it or below it or whatever that eventually will tell you I'm good enough. So like the algorithm will be correct. However, your mesh has hundreds of millions of triangles, so it has millions of clusters. Let's say the mesh is far away. So you only want to render it using a few very coarse clusters. And so you want to select a total of like 15 clusters. But your tree has millions of them, so it's very inefficient. And you have to do this per object, that's the important thing. If the mesh is instanced like 100 times, every instance of the mesh may have a different cut through this tree that it renders at, right? If you have a mesh that's closed versus far, like it's a different set of clusters. So there is a very easy way to build this, which is you have a compute shader that goes through every cluster, asks this question, good enough or not, and then adds the cluster to the render queue or not. But it's going to be very slow. And so, how far do you want the efficient way to do this? There is an efficient way to do this that's documented in the so people who are interested in Nanite, I feel sorry for the amount of time that you'll have to spend on this, but the reference, not documentation, like the talk is, there is a talk by Brian Harris who invented the technique. I think from SIGGRAPH 2021, I forget what it's called, like Nanite something, and it talks about the runtime difficulties there. But so it talks about a way to do this selection of cuts efficiently on a GPU. A, it's quite complex. B, my recollection is that the way to do this optimally relies on undefined behavior in the GPU computing model. So there's this thing in compute shaders that's called forward progress guarantee. That's poorly specified. And it's basically this. If you have a thread, so you can implement a spin lock in a compute shader, like, sometimes you need to. The spin lock could just be the traditional CPU-like spin lock, like you read the value is like 1, means somebody else has the lock, you're like, oh no, I'll ask again, and then you spin until it becomes 0. Is a spin lock safe in a compute shader? And the answer is it's very complicated. And so my recollection is that the optimal way to do this Nanite Nanite hierarchy classification may rely on some things that are not like fully specified in the same way that spin locks aren't fully specified. Because you are trying to map a very complex algorithm, not the one that I described. The one that I described that does a per cluster work is very simple. But what you want to do is somehow in parallel, traverse this hierarchy across many different threads and somehow do little wasted work, but do this in a way that's safe to do in parallel. And so doing that level of detail, right, could take you months. Now, do you need to go all the way down there to have a functioning render? No. But if your goal is to compete with Unreal on performance, then the answer is like months for sure of runtime work. So it's a very, very, very deep rabbit hole. But it's basically a replacement of the whole rendering pipeline sort of before the G buffer. So it's like there's a lot that goes in it because there's like forms of calling and stuff like this. It's just, it's just complicated. But yeah, the world was simpler before people do Nanite, and now the world is more complicated.
glTF ecosystem in meshoptimizer. Then can you tell me a bit about that?
All right, so I mentioned in the very beginning that meshoptimizer is like 3 projects in the French code. We talked about 2 of them, and then the third one is glTF back. And I guess there is also maybe it's 4. So there's glTF back, and there's a related thing, which is you can take some of the meshoptimizer code and run it in JavaScript. So, okay, there's kind of 2 reasons why meshoptimizer even has a connection to glTF. So one is I'm just interested in glTF. I think it's a nice format. It has some downsides, some upsides, but I think it's, the alternatives to glTF I like much less. And so glTF, for people who don't know, it's a Chronos specified format which you can use to store mesh and scene and animation and texture data. It's more than a mesh file. It's more like a scene file format. And you can store it in a reasonably compact way. glTF is a JSON plus binary file. So JSON segment of the thing specifies like the high level. You have a node hierarchy in glTF, and so this node hierarchy is represented in the JSON component of glTF. But all of the binary stuff, like the vertex buffers, the index buffers, the animation data, all of that goes into the binary file. So it's reasonably efficient to load it. It's still not. It's general, so I don't think it's always appropriate. It's like, I think usually I would not pick glTF as a runtime engine storage format. It's very rare when this is appropriate, but this is not because glTF is inefficient particularly. It's because it's general. We talked about the Vertex formats, like, you may want to have a custom normal storage thing or whatever. glTF doesn't support this, but also it forces you to support permutations of, it's like, positions could be that format or could be this format. Texture coordinates may be there, or there may be 2 sets, or there may be 0 sets, who knows? So you can write a renderer that natively supports glTF. It's just if you wanted to write the most efficient renderer in the world, you'd want to have a lot of constraints that glTF doesn't allow you to format the data this way, or forces you to deal with all of the other variations. But I think it's a nice format. If you want to work with that format, so there were kind of 2 problems for me. One is I was looking at glTF, and I looked at the state of all of the efficiency things that I worry about, right? And I was like, well, all of this is not great because you get a random glTF file. It has duplicate vertex data. It doesn't have vertex hash optimization, which you think it doesn't matter, but it does matter. Because you take a glTF file, you load it in the browser in your renderer of choice. Well, whether or not this file has been optimized, has index data that has been optimized for vertex cache or not, directly affects the rendering performance on a desktop GPU, right? So glTF didn't support quantization very well. It supported it a little bit, but mostly not. So I looked at this and I was like, okay, so one, I don't love the state of where glTF files are, even from the perspective of the web ecosystem. So let's ignore the native stuff for a little bit. Let's assume in native world you have, even if you have glTF files as an input, you have custom processing pipeline. In web world, people like to just render glTF files. Well, it would be nice if the files that they were rendering were efficient. 2, so meshoptimizer is a library, right? One generally difficult thing to do is you can't develop a library in isolation. I don't know how people do this in other libraries. It depends on what you do. If you have something that's contained, if you have a PNG loader, you could develop a PNG loader with just a basic unit or like an integration test suite that just loads PNG files, right? But the meshoptimizer is like a toolbox. And one of the questions that I have about the toolbox is it easy to use? Is it sufficient to fully implement an engine, processing pipeline, etc.? You kind of want to have an engine built around this, not because I want to build an engine, but just because you want to fully stress all of the ways in which it can be used, right? And so glTF seemed like a way to both have like this end-to-end pipeline that uses meshoptimizer so that all of the algorithms can be exercised in that context. And also like glTF, could be better. So when I started going there, I realized, so because of this, I built glTF pack. glTF pack is an application. You give it glTF file, it outputs a glTF file back. It runs all of the meshopt algorithms that we talked about. It does quantization for you based on what it considers to be okay, not good, in the sense that, as we discussed, like the perfect choices depend on the use case, right? So it's difficult to have kind of globally perfect idea of what to do, but it does some things. And it also does a bunch of scenery organization that is kind of outside of the bounds of meshoptimizer, but it's like things like you have a material, and the material has alpha blending enabled, but your textures attached to this material do not have an alpha channel. This means you are wasting CPU cycles enabling the blending unit, even though the pixels should not be blended. And also you sometimes are causing visual artifacts. And this type of problem is common in some glTF files in the ecosystem. So there's this tool that exists, but when I started developing this tool, I was like, well, I want to do a bunch of things that glTF doesn't want to let you do. For example, glTF didn't have a way, so it had a way to, so colors, vertex colors, could be quantized in glTF, and I think maybe texture coordinates, maybe not, but normals did not have a quantization format sort of in glTF. Which was strange. It was just an omission. I think when they specified the format, they forgot about this or whatever. They remembered for colors. So colors you could do 8-bit. Normals you could not. So normals you were forced to use. Oh, and glTF also has to support WebGL 1.0, or at least had to, as a baseline like expectation of what the GPU can do. And WebGL 1.0 does not do half precision floats. So glTF didn't have half precision floats. So it didn't have quantization support, and so I was like, well, I want to fix this. So I ended up actually contributing 3 extensions now. So I contributed an extension to glTF ecosystem, which allows use of quantized formats for the Vertex data, which then allowed glTF pack to use this. But it's not glTF pack alone that does this. There is another tool called glTF transform that uses meshoptimizer for some stuff, but it's like a separate TypeScript-based application that does glTF processing. It also does quantization. So I contributed this, and also I contributed an extension, so it's like 2 extensions now, for the compression that we talked about. So the compression that we talked about turns out to be a fairly reasonable fit for the web too. They have an alternative mesh compression from Google, and it's part of glTF spec. But the problem with this is it's quite slow to decompress. So it goes into the problem that we talked about. It also, so when you run code on the web, you either run it in JavaScript or WebAssembly. The modern way to do this in WebAssembly. But even with WebAssembly, if you have complicated code that you want to run, it's a large binary that takes the browser a while to JIT on the first load. The process is cached usually, but the first loads are important on the web, because I give you a website, you go to the website, it has a bunch of 3D geometry, and then it's the first time ever that you've seen that domain. And then domain happens to bundle a few decoders for compressed formats, because browsers don't support these things natively. And if these decoders are hundreds of kilobytes of WebAssembly, then these things take half a second or whatever to JIT. Is half a second a lot of time? Well, it's a lot of time to delay your first page load, complete page load for, right? So, and my decoder turned out to be fairly good for this purpose, because it's under 10 kilobyte of WebAssembly. It's very, very compact and it's very fast. But so my Vertex decoder, decompressor, the reason why my decompressors are fast, the one that I'm working on right now is crazy in that regard, but even the Vertex compressor, it's using SIMD fairly aggressively. And WebAssembly had SIMD support, or it had emerging SIMD support via separate extension. but it didn't have like a couple instructions that I think were just generally really powerful, and like every SIMD instruction set has instructions like this and should have. If they don't, I'm not sure about RISC-V, but like, so ARM has an instruction. The most important instruction in SIMD is called P-SHUF-B, shuffle. And it's basically a thing where you give it a vector and you give it another vector that is determining indexes in the first vector that you should pull out. So it's like a table lookup that you do in every individual SIMD lane in parallel, and it's super efficient. It's like one cycle, I don't know, it's like very, very fast. And you can express so many weird problems with like this single instruction, and they didn't have this. And I was like, well, if they don't have this, I'll just be sad because the SIMD instruction set in WebAssembly is going to be worse. B, I will not be able to port my amazing Vertex decompression code to this without it running without SIMD, which is much slower. So that's a problem. And so it's kind of funny, but as a byproduct of all of this, I ended up contributing so both to glTF and to WebAssembly. So the instructions are now part of WebAssembly SIMD.
Nice.
And then there are the couple extensions that are part of the glTF spec. And I should mention it's kind of interesting because both glTF and WebAssembly were quite friendly for like an unaffiliated contributor. Like, usually, so if you look at the Vulkan specification process, to contribute to that, you basically have to work at a company that is like a graphics card company, because then you can like be in the right places and talk about the right things and try to force change. But if you are an external person, it's hard for you to contribute to Vulkan. And I expected that it would be hard to contribute to WebAssembly and glTF, but actually it's like the experience is quite pleasant, I would say. Kind of to go all the way back, you take glTF back, it can produce a glTF file, and that glTF file can then use these extensions. So then you open this glTF file in your web browser, and then if it's compressed, which is optional, but if it's compressed using meshoptimizer algorithms, then you load like an extra like 6 kilobyte file with like WebAssembly in it, which decompresses this on the fly for you and then puts it in like the actual Vertex buffers in your WebGL context. So this is kind of fun. I spend less time on this than I used to, just because I think it's mostly because you're constrained by what glTF can and can't do. I've implemented like glTF doesn't do meshlets. It doesn't even have level of detail officially. There's like custom extensions, I guess, but in that sense, the format, the tool, glTF pack tool is like more complete because the format is like more stable, and so it's easier to get to a point where you look and you're like, well, I don't know what else it's missing, right? It's kind of mostly there.
Nice.
But yeah, so because of this, I mentioned all of the various languages. meshoptimizer. So I don't maintain any of the bindings to any of the languages like other people have. Rust bindings and Zig bindings and C# bindings. The JavaScript ones, unfortunately, I maintain because they're kind of part of this whole like web system. But
I've seen that there are bindings. Jonathan,
oh, nice.
So
nice.
See that meshoptimizer there as well. All right then. After 3 hours of technical chat on this,
Yes.
I want to ask you a couple of questions that are a bit higher level regarding the library specifically.
Mm-hmm.
How the heck the library is open source with MIT license and free for everybody to use? Like, how did it happen that you chose this model? You choose this model for the development, and like, how are you doing this? That you're working full time on it when this is like not a commercial library.
So there's a few things to say. So I mean, I think in general it's open source because I kind of believe in open source model more than I believe in closed source models. We are having this conversation. I'm running Linux right now. I did have to install Chromium because Firefox didn't work for the podcast thing, but but even Chromium is open source. Some parts of the stack are closed source. But the reason, so I think I in general tend to err on the open source side, not because of sort of ideological concerns, but more because of practical. So now I use an editor, and I sometimes find bugs in my editor or things that annoy me. Being able to go look at the source code, find a bug, fix the bug, submit a pull request, and see it fixed means that you're kind of more in control of your entire environment, right, than you would otherwise be. Some of these things are impractical, but I patched, so I use NVIDIA right now, which unfortunately does not have an open source driver. But while I use the AMD GPU, I ended up contributing a couple patches to the AMD open source driver. So being able to observe and occasionally fix the stack, I think in general, super valuable to me. Because of this, I always liked open source, right? And meshoptimizer, so when I built meshoptimizer, I worked, I guess, at Roblox at the time, but the way that it got created was kind of like this. So I solved problems like this before in my professional career using some mostly existing libraries that I just didn't like. They were just not very good. And some proprietary stuff, I think, that just became obsolete. And then at some point, I find myself in this company, it's like, okay, I have to do a bunch of stuff. Some of this I know how to do. Some of this I had code for my pet projects from my engines, just it wasn't in the library form, it wasn't working very well, stuff like this. So then you have two options. You can write the code for the company that you work for. It's going to be proprietary, it's going to be owned by the company because you're doing this on the company time and stuff. And then you quit the company, you join some other company, you have to solve the problem again. What the hell are you going to do? Nothing, I don't like solving the same problems multiple times. So I think I was just thinking, well, I have this problem. I can't recommend an existing library. If I were asking myself, how do I solve this problem? Can I use some other library? I was like, I don't know. There's nothing for me to recommend, so I guess I have to do this. But if I do this as closed, so if I just do this as part of my company's job, then it's going to be closed source and not great. And I think in general, I think the more I work on all of these things, the less I like the company and product boundaries, and the more I like the sort of lifting all the boats type of work, where you can make a thing that gets integrated into a bunch of stuff, and that gets better as a side benefit, right? And it's just more interesting to me to do that kind of work compared to it's like, oh, there's this specific thing that we need to solve for this specific product, and that product is going to launch, and then in 5 years this product is going to be dead and the company is going to close, and I guess it's like nice memories, but nothing else, right? So this is how it started. Now, I've worked, so I think for the last year and a bit, it's not full time, but I work on meshoptimizer a lot. But meshoptimizer became useful and popular sort of before I started doing it full time, right? So the before this, I just did this in the evenings and stuff like this. And then it became big, and then I quit my job, and then I was like, I don't know what I should do. And then Valve reached out, and Valve is like, well, we'd like to sponsor meshoptimizer, I don't know, we don't know what your plans are, but so right now Valve sponsors the development of meshoptimizer, and that kind of helps me justify not really having to do anything else, right? I do other, I guess, unpaid open source work too, but this is good in that sense. It allows me to focus way more on, we talked about the simplification stuff. The simplifier was in an okay shape before last year, I guess. But I think what really pushed it over the line was basically me saying, well, I want to solve this problem to the extent where I don't have to, feel guilty of the result. How do I do this? Like, how do I make sure that it actually works? And, a lot of stuff happened since, a lot of improvements have went in since that kind of got it way closer. But yeah, so the project, this is not a recipe for success for open source, right? Because if Mesh Optimizer didn't exist, then nobody would use it. And if nobody used it, nobody would be happy to pay money for it, right? And then the other side is Valve is fairly unique in that there's a few companies that do open source sponsorships in ways that matter. There is companies that do small open source grants, but small open source grants are basically impossible to use to kind of replace your full-time job with, right? Which is unfortunate because, and then the other side is you can, so when you do open source, there's other open source projects that have corporate sponsors and, it's fine. You had an interview with Omar
Yes.
on I Am GUI who has a lot of corporate sponsors. One thing I never liked, and I continue to not like, and I try to spend zero amount of hours on it, is the whole aspect of sales and so
marketing.
Let's say even Mesh Optimizer was commercial, right? There's separate issues with commercial projects where I think it's just much easier to sell, quote unquote, to have an open source project integrated than it is to do a commercial one. Because commercial one, even if you're internally inside a company, integrating a library that's open source, as long as it's license compatible, you add it, you're done. Sometimes you have token legal review that looks at the license says MIT, they're good to go. If you want to integrate a commercial project, even if you really like it, even if there's nothing like it on the market, etc., it's oh wow, budget reviews and legal reviews, and we need to draft contracts, and it's a lot. And then flip it, and then ask it from the perspective of the person who is trying to sell the project to a company. That's super frustrating because there's tons of companies. Companies have demands. Companies want things. Some companies will tell you that they want a thing before they are going to agree on a license. You're going to go on, work on your own time, add a feature, and then actually, we don't need it. Or they'll ask you for one more feature. So it's, and you are spending so much of your time kind of thinking about this, right? It's which companies should I talk to? How do I structure my offering in a way that makes sense, etc. So I'm fortunate to not have to do any of this. And part of why is kind of Mesh Optimizer started and got big and popular while I just had a job. And now that it's big, you can occasionally find these great companies that can sponsor a project in a reasonable manner. And sort of the other important thing is, there are some companies that do it right, but again, often in open source, even if you see funding, the funding is strings attached. It's so I think my understanding is SQLite works like this, where they have a tiny team that's worked on the library forever. It's super big, it's super popular, right? It's I don't know, billions of installs. Every Android phone has it, every iPhone has it, etc. My understanding of their model is there's things that SQLite doesn't have. A company goes to them and says, hey, we'd like SQLite to support the feature. And they're sure, that's going to be whatever, however much it's worth. And, it's a transaction, right? That's a bad model for open source in general, I think. Now, works for SQLite, presumably, so that's great for them. But what about features that you don't need yet? What about maintenance that you don't consider important, but if you don't do this, the library ends up dead? One example is the mesh shader stuff that we talked about. When I added it, nobody was using it, which sort of makes sense in some way. There's a new hardware feature. To use a new hardware feature, you need to have robust tooling support and robust hardware support. Robust tooling support didn't exist because nobody implemented it. Robust hardware support didn't exist because the feature was new. Okay, so let's say hardware support did exist, but tooling didn't. how do you add a feature? Well, you need tooling support. Tooling support doesn't exist. It's a catch-22 problem, right? So the way I solve the catch-22 problem in Mesh Optimizer, I'm excited about the feature. I'm going to build support for it. I don't particularly care if people, I care if it's useful, but I don't care that nobody is using it right now because I think people might find it useful in the future, right? So I built it, and then games started shipping with it at some point after, right? So it's like, and my argument is always that for companies that do open source sponsorship truly, that believe in open source, this is the good model that they should also be excited about, because for every feature that you don't need, that other people might, there is a feature that will help you if you had it, but maybe it's not front of mind or something like this, right? And like maybe in a few months, you will need a feature that other people have needed before you. And if this feature doesn't exist, your project might be at risk of being delayed because the implementation doesn't exist yet. It needs to be implemented, and then it needs to be tested, and then maybe it doesn't work very well and stuff like this, right? So it's kind of counterintuitive, but I think but it's almost similar to the algorithms that we talked about. Like, local optimum gets you so far, but if you think from the global perspective, it might be better for you to do something that's not optimal in the moment because it makes things better for everybody else. So.
Okay.
But yeah, I'm happy I can do this, but I don't know that this is a recipe for, there's other examples similar to this, I'm sure, but I think fundamentally it relies on you kind of somehow finding the time for building a large and successful open source project, and then suddenly finding yourself with the problem of, people want to use it and they actually care about it existing enough to pay money. And it's like, okay. Interesting. I don't know how to replicate this. My other open source projects are not funded, so.
I'm assuming that because it's open source and also has like MIT license, you might not know about usages. Like you probably don't have like 100% idea like how often it's being used. But GitHub recently has added this feature of like uses. I don't know how it's being counted.
So this is.
It has 172K usages. Mesh Optimizer, which is clones or like something. So can you tell me a bit more about the usages, adoption, popularity, and stuff?
Okay. Misleading. I love misleading numbers because they're great at impressive people for their own reasons. But so many things to say here. So first of all, the thing that GitHub is computing is based on the JavaScript NPM ecosystem. So this is the reason why it's so high is because people use the JavaScript glTF related stuff that I was talking about often, and then it propagates through. I think like there are some renderers that depend on Mesh Optimizer by default, which then propagates into all of the little side projects that people use and stuff like this, right? So I think that you can sort of ignore it's a web ecosystem. It's kind of difficult to estimate. So in the gaming space, there is a few things to say. So one is it is very widely used. My assumption, so it's not used in Unreal or Unity, even though I think both would benefit from it in some places, but it's like whatever. It is used by most proprietary engines, not all, most. I don't know. I don't have a count. It's difficult to know. So one reason why it's difficult to know is the way things are supposed to work in the open source world is a game uses a library uses MIT license. The library gets mentioned in the credits, in the giant credit screens that nobody reads, but I do. And, everybody's happy. There is a couple things. One is there's a lot of uncredited usages of open source in game development. Just because people don't think about this, the license technically MIT license kind of asks for attribution, but it has never been legally challenged. So like nobody knows if you can sue a company for not mentioning an MIT library, in the credits. For Mesh Optimizer, the problem is like even more acute. Which is to say there's many libraries that ship in many open source games that aren't often credited. For Mesh Optimizer, the problem is more acute because it's usually used in the processing pipelines that you don't ship to your users. So there's no obligation to mention it in the license screen, so people don't. So because of this, I don't really know. My usual experience is I go to a conference, I have a chat with somebody, they work at a AAA studio with proprietary technology. They're like, thank you for Mesh Optimizer, we use it. I'm like, tell me more. First time I've ever heard about this. Mesh Optimizer is used in Zelda and Tears of the Kingdom, the second one, the most recent one. My understanding is they use the compression, and so because of this, they had to mention the library because they linked to it at runtime as part of their third-party notices. But their third-party notices aren't in the game; they're all on the website. So I basically learned about this because somebody pinged me, and they're like, "Oh, I looked at the Nintendo license notices for Zelda, and your library is in it." I'm like, why would you ever look? But thank you. These things bring me when I learned that the library is useful, it's super cool. But I don't have a perfect visibility for sure. But yeah, there is some proprietary engines that probably don't use it, right? I'm sure, but a lot do. But a lot do in multiple ways, right? So again, it's a set of tools. So maybe you don't use some tools, but you use others. It depends on what's useful to you. But yeah, so it's quite widely used in the industry. It's just that I don't know how much. There are some companies that are very gracious and kind of disclose the usage as in they put the library in the license screens. Baldur's Gate 3 uses Mesh Optimizer. They put it in the license. Alan Wake 2, as I mentioned. So Zelda, there is a bunch of games, but it's literally at this point I don't fully know because I either have to talk to somebody or sometimes the company publishes a conference talk, and they're like, there was a recent example where a company published a conference talk and they're like, they described their meshlet processing pipeline, and I knew about the talk because I looked at the conference slides or whatever, the talk summary. I'm like, these guys are using meshlets. I wonder if they use Mesh Optimizer. So I watched the talk. They don't have it in the slides, but in the captions, the speaker is like, oh, and for this we use Zeux's Mesh Optimizer. I'm like, yes, great. But this is you kind of learn about this by proxy because the library is mostly kind of offline, right? I have another popular open source library that is more used at runtime for some reason, even though it shouldn't be. And for that, I have way more game credits just because, I don't know, just because people link to it at runtime. So because of this, if you use Mesh Optimizer, A, you should add it to credits, of course, but B, you should use compression. A, because it's good for you, B, because it will force you to link Mesh Optimizer to your runtime code, and then it will force you to disclose the fact that you use Mesh Optimizer. So, again, it's like a win-win situation. But yeah, there is no other, and the other thing, of course, to note is that a lot of the open source engines use it, right? So for proprietary ones, you don't know. For open source, you do. Godot engine uses it. I don't really know. So out of the big ones that I remember, there is Godot and Godot uses. I don't actually know what the big open source. Oh, Bevy uses it through the Rust bindings. There is I'm sure others, but there's a lot of engines these days. So
since it's open source and already has a couple of contributors on his GitHub page, is Mesh Optimizer accepting contributions? And if so, how do you suggest people go about contributing?
So Mesh Optimizer is accepting contributions. However, the one thing I find is, so contributions to Mesh Optimizer tend to be difficult to do because the problem space is kind of intense a little bit. So all of these problems are difficult to solve. There are some things that the library doesn't have, and sometimes it doesn't have them because I haven't gotten around to them, but sometimes it doesn't have them because it's difficult to engineer an algorithm that's generally useful and stuff like this, right? So there's some implicit if this feature doesn't exist, why not? And then in terms of the code, so it's written in C++, but it is a C++ without dependencies. There's no STL. I depend on the C library in the sense that I use like memcopy. So memcopy is good. If you use memcopy, your code will be accepted. But there is no other dependencies, which means it's a little bit hostile in the sense that, so my whole paradigm here is if I spend more time on engineering the library very well, then everybody who uses the library gets the benefits for free. But kind of by nature, this makes development of the library more complicated, right? No dependencies, the code has to be fairly optimal. Not in the sense that there are some things that like decoders that are very optimized. The rest of the library isn't like micro optimized to death, but it's like, it pays a lot of attention to performance, right? So I think this combination of this is a difficult space, there's a very high quality bar, and things that the library doesn't do yet, it usually doesn't do them for a good reason, and things that the library does do, they usually pretty good. Then the combination makes it kind of difficult to contribute. So my preferred model is usually that if people have a thing that doesn't work or they think should work or whatever, then if it's a bug, they should like start an issue about this, and if it's an idea for a feature, then they should start a discussion about this. GitHub has like a separate issues versus discussion thing. And then we can talk about this because sometimes, I sometimes get a pull request for a feature that actually is supported already, but maybe the documentation wasn't clear enough, or maybe the person didn't read that carefully or whatever. And it happens. It's not a problem, but it's just that I think when you start with a pull request, I think in general, it's a bad dynamic, because then you're like, oh, I spent all this time working on this amazing contribution. Why do you not accept my amazing contribution? I'm like, well, we should have talked about this first because it's complicated, right? So, which is all to say, so contributions are welcome, but I think most of the library code, vast majority of library code is written by me, and I don't have a problem with it. And it's just that, if people want to start, if people want to have something that the library is missing, they should open a discussion channel somehow, and then we'll see, right? Sometimes, maybe it's like a thing that's already on my roadmap and I have a clear idea of how to do it, and I'd be happy with somebody else doing it. But sometimes it's just difficult. It depends, I would say. But yeah, I do get some amount of pull requests. I get more pull requests in glTF pack than I get in meshoptimizer, because there it's friendlier to contribute, it's easier to write code in and stuff like this. So that's fine. And sometimes things are just hard. Somebody opened an issue actually around simplification like a year ago, maybe or more, where they're like, okay, so this code can be tweaked in this way to make this better. And they're right, but I still haven't done this. This was not a pull request, but it's just an example. I still haven't done this because I tested it, and it makes it better on their on their use case, but it also blocks a bunch of simplification code in ways that are very harmful in a bunch of other cases. And I don't have a way to reconcile these two things cleanly, right? This is, I think, in general difficulty in meshoptimizer. It has to be generally useful, and if there's a thing that's helpful for one case and harmful for another, I have to somehow reconcile that. Sometimes I end up having two algorithms, like we were talking about the clusterization. There's two algorithms because two use cases are different. But sometimes there's just not a clean way to figure out what to do here, right? So I think it's just naturally difficult to do some of this stuff, unfortunately. But it is what it is. If people want to improve documentation, that's always easy, but honestly, that's not it's not super high profile. But yeah, I think from perspective, meshoptimizer is not that friendly. When I started meshoptimizer, I wanted a very high density of code quality. I wanted to say complexity, but that's not quite the right word. But I wanted basically to focus on the internals being very tight and very good. And this means there is very little surface for code that's like, would be nice to have, but is a little bit half-baked, but it's fine, we can figure it out later, stuff like this, right? Which I think by nature makes it difficult for first-time contributors to any code base, not meshoptimizer, because there is just little surface area for things that are not technically like intense and require a lot of background and also a lot of coordination. So this is another thing with PRs. Always start a conversation with maintainers of the repository before sending them a PR, because there's just going to be way fewer like unpleasant surprises and bad feelings on both sides. Honestly, it's just it is what it is.
Okay. All right. Awesome. Arseny, this was super cool. I initially had this idea that we're gonna have like a hour-long episode about just Mesh Optimizer, and it's like 3 hours in, like we're done with the Mesh Optimizer.
We did have an episode about just Mesh Optimizer, so
Yes.
you achieved half of your objectives. I think that's good.
Yeah, exactly. That's a good way to look at it. Can we do the shout out for your social media blog? Like, where can people follow your work?
Right. So the blog is at zoox.io. So social media is complicated these days. I usually post on Mastodon, where I don't really know. Mastodon has this decentralized, but basically, I think if you go to zoox.io, I think it has Mastodon and Blue Sky, but I am in theory on Mastodon, Blue Sky, and Twitter. I'm usually signed out of Twitter though, and I usually don't use Blue Sky much. So if you want to actually talk to me, basically go to Mastodon, but you could follow me, on either of these three. And my blog is I don't blog very often, but I try to blog like a few times a year with, some sort of meaningful and I think interesting work that people would find fun to read about. For example, so we talked about clusterload.h. So there's a blog post on zoox.io that talks about some of the challenges in kind of building this higher level pipeline and making it fast and all that stuff. And there is some other stuff. I think I have a meta blog post, I think from last year, that links to all of the Mesh Optimizer relevant articles on my blog post. So if you just go to that, you should have a few hours worth of reading material for you.
I will also highlight just Mesh Optimizer docs as a resource to go through, to sort of understand, fill in the blanks regarding the GPU work every now and then. And then also, you have tremendous series on Vulkan on YouTube, and you have a lot of other videos and streams, right? Do you actively want to do it, or like how's your relationship with streaming? And
I occasionally stream. So I started this series I think in 2018 or so. Basically when mesh shaders started, I think actually mesh shaders may have been the motivation, as in like there's this new hardware feature, it would be fun to experiment with this. And if I did, I could blog about this, but there's this whole new medium of people writing code, and for some reason people like watching people writing code. So I'm like, this is interesting, I should explore this just for fun. And I ended up doing, I think it's like 30 streams or so by now. But the way this works is, so I have a small renderer project, and whenever there's a thing that's adjacent to Vulkan or rendering that I think could be useful for me to explore on stream, then I have another stream. But it's not regular, and it's not, we just talked about the process of writing a runtime for Nanite. I like the streams where I have a good balance between not knowing what I'm going to write and knowing how I'm going to write it. Like exploring a completely new area on a stream is just going to be me being miserable for 2 hours that it takes to do a stream. And also I tend to think worse when I'm on stream. And that's just kind of, it means I take longer to solve problems, but also if I get stuck, I might not get unstuck, right? And maybe there's not a problem with it, but it just feels a little bit miserable to I know I can solve this, but I have to do the stream. Oh my God. So it usually has to be a thing where I can explain and implement on a stream in a way that's reasonably accessible to people. And there were a number of topics like this. but they don't happen that often these days. So like whenever there's some other thing that I decide would be good for a stream, I do it. But it's not like a routine, and it's not, I don't plan to like start doing that on a regular cadence or anything like this.
Okay. All right. Very well. Super cool, Arseny. Thank you so much for walking me through all these algorithms. This is really nice.
Thanks for having me, and for bearing with long explanations of things that might be interesting to people.